We often believe the digital age stands alone at the summit of human ingenuity, yet buried beneath the sands of time lie artifacts that shatter this illusion and prove the blueprint for the modern world was drawn millennia ago. Imagine a reality where steam engines hissed in ancient Alexandria, where Roman glassmakers mastered nanotechnology long before the microscope, and where a bronze computer calculated the cosmos centuries before Silicon Valley existed. These are not myths, but tangible archaeological evidence of a forgotten technological zenith that challenges everything we know about the timeline of progress. In this deep dive, we strip away the superstition to reveal the raw engineering behind 6 impossible artifacts, from the seismic precision of Han Dynasty China to the electric mysteries of Babylon, demonstrating that the gap between the ancient world and the 21st century is far smaller than we ever dared to imagine. The timeline of human history is frequently misunderstood as a single, unbroken ascent from primitive squalor to modern sophistication. Conventional wisdom dictates that our ancestors lived in a world defined by simple tools and brute force, slowly grasping the basic levers of physics over thousands of years until the sudden explosion of the Industrial Revolution. We tend to view the past through a lens of technological condescension, assuming that without electricity or silicon, there could be no true complexity. However, the physical evidence buried beneath layers of sediment and preserved in the quiet corners of museum archives tells a radically different story. When archaeologists brush away the dust of millennia, they often uncover anomalies that defy this linear narrative. Devices that seem to have fallen out of time, artifacts that display a mastery of engineering, chemistry, and astronomy that rivals the capabilities of the 21st century. This exploration centers on 6 specific discoveries that challenge our fundamental assumptions about the trajectory of human innovation. These are not mythological relics or misunderstood ritual objects, but functional hardware designed to solve complex problems. By examining them, we uncover a hidden history of science, where the principles of inertia, nanotechnology, electrochemistry, and analog computing were not only understood, but applied with startling precision. The first of these anomalies brings us to the imperial courts of Han Dynasty China, where the need for disaster management sparked a leap in mechanical engineering. Zhang Heng's Seismoscope, a bronze vessel adorned with dragons and toads, stands as the world's first earthquake detector. While it may look like a decorative urn, its interior housed a sensitive pendulum mechanism capable of detecting the direction of seismic waves from hundreds of miles away. It functioned on the principle of inertia, triggering a release mechanism that dropped a ball into the mouth of a metal toad, alerting the court to disasters that had not yet been felt in the capital. This was not magic. It was seismology applied through exquisite bronze casting. Moving westward to the workshops of the Roman Empire, we encounter a mastery of materials that modern science has only recently begun to comprehend. The Lycurgus cup, a glass chalice depicting the death of a mythical king, offers a lesson in ancient optics and chemistry. To the naked eye, the cup appears green, but when light passes through it from behind, it transforms into a glowing ruby red. This dichroic effect is not the result of dye or paint, but of gold and silver nanoparticles suspended within the glass itself. Roman artisans had achieved a mixture so uniform and precise that it effectively constitutes an early form of nanotechnology. They were manipulating matter at the atomic level to control the behavior of light, a feat that requires us to re-evaluate the sophistication of ancient Roman industrial processes. Further disrupting the timeline is a discovery from the sands of Mesopotamia that suggests the harnessing of energy predates the invention of the light bulb by thousands of years. The Baghdad Battery, a modest ceramic jar containing a copper cylinder and an iron rod, presents a compelling case for the ancient use of electricity. When filled with an acidic electrolyte, this configuration creates a galvanic cell capable of generating a weak electric current. The existence of such a device implies that the chemical generation of power was known to the Parthians or Sassanids, likely used for electroplating gold onto silver ornaments. This shifts the history of electrical engineering from the laboratories of the 19th century back to the dusty workshops of antiquity, proving that the utilization of electron flow is not exclusively a modern privilege. Perhaps the most staggering challenge to our historical model comes from the bottom of the sea. The Antikythera Mechanism, recovered from a shipwreck off the coast of Greece, is often described as the world's first computer, but even that title fails to capture its anomaly. It was a shoebox-sized device packed with at least 30 bronze gears, programmed to calculate the cycles of the sun and moon, predict eclipses, and track the timing of the Olympic Games. The precision of its gear teeth and the complexity of its differential gearing system display a level of mechanical genius that would vanish from the Western world for more than 1,000 years. It demonstrates that the ancient Greeks were not just philosophers and geometers, but advanced mechanical engineers who could translate the mathematics of the cosmos into physical, rotating realities. The investigation continues into the realm of automation and robotics, concepts we usually associate with the digital age. In the bustling metropolis of Alexandria, the engineer Hero designed machines that blurred the line between magic and mechanics. His automata included temple doors that opened automatically when a fire was lit on an altar, utilizing the expansion of heated air to displace water and drive a system of weights and pulleys. He also devised the world's first vending machine, a device that dispensed a measured amount of holy water in exchange for a coin. These inventions prove that smart systems do not require microchips. They only require a profound understanding of hydraulics, pneumatics, and mechanical advantage. Finally, we confront the most tantalizing what-if in the history of technology, the Aeolipile. Also described by Hero of Alexandria, this spinning copper sphere was a functional steam turbine. Heated water produced steam which escaped through angled nozzles, generating thrust and causing the sphere to rotate rapidly. It was a demonstration of jet propulsion and the conversion of thermal energy into kinetic motion. The fact that the fundamental engine of the Industrial Revolution existed in the 1st century AD forces us to confront difficult questions about why technological breakthroughs do not always lead to societal transformation. Understanding these artifacts requires a methodology that goes beyond simple observation. We must strip away the sensationalism that often surrounds ancient mysteries and apply rigorous scientific analysis. This involves the use of X-ray tomography to peer inside the corroded remains of the Antikythera Mechanism, allowing researchers to count gear teeth and reconstruct the device's logic without damaging the fragile original. It involves mass spectrometry to analyze the chemical composition of the Lycurgus cup, confirming the presence of gold and silver colloids. Furthermore, experimental archaeology plays a crucial role. By building faithful replicas of the Baghdad Battery or Zhangheng's Seismoscope using the materials and tools available at the time, we can test their functionality. We can measure the voltage produced by the jar or the sensitivity of the pendulum. This approach transforms historical speculation into engineering fact, proving that these devices were not merely theoretical curiosities but working machines. The significance of these discoveries lies in their ability to shatter the illusion of inevitable progress. They reveal that the path of human knowledge is not a steady climb but a jagged landscape of peaks and valleys. The existence of the Antikythera Mechanism proves that a high-technology civilization can collapse, and its knowledge can be utterly lost. The specific mathematical and metallurgical skills required to build such a device disappeared, leaving humanity to rediscover them painfully over the course of centuries. This serves as a stark reminder of the fragility of information. We often assume that once a discovery is made, it remains part of the collective human library. But history demonstrates that wars, economic collapse, and shifting cultural priorities can wipe the slate clean, resetting the clock on scientific advancement. Contextualizing these inventions also requires us to look at the economic and social structures of the ancient world. The Aeolipile, for instance, highlights the disconnect between invention and application. While the Romans possessed the steam turbine, their economy was built on the back of abundant slave labor. There was no economic pressure to mechanize production, no capitalist drive to increase efficiency through machinery. The invention remained a novelty, a toy for the intellectual elite, rather than an engine of industry. This teaches us that technology does not exist in a vacuum. It requires a receptive society to flourish. An invention can be brilliant, functional, and revolutionary, yet fail to change the world if the economic conditions do not demand it. These 6 artifacts, the Seismoscope, the Nanotechnology cup, the battery, the computer, the automata, and the steam turbine, serve as the focal points for a broader investigation into the lost capabilities of our ancestors. They force us to abandon the chronological snobbery that places the modern world at the apex of intelligence. Instead, we must recognize the ancient engineers as our intellectual equals, individuals who looked at the natural world and found ways to harness its power with the materials at hand. They understood the invisible forces of the earth, the microscopic properties of light, and the mathematical rhythm of the stars. As we examine each of these technologies in detail, we are not merely cataloguing museum pieces, we are reconstructing the intellectual landscape of the past. We are seeing how the need to predict earthquakes drove innovation in China, how the desire for beauty drove chemistry in Rome, and how the obsession with the heavens drove computation in Greece. This is a study of human ingenuity in its rawest form, unassisted by the accumulated knowledge of the intervening centuries. It is a testament to what the human mind can achieve when it is forced to observe, hypothesize, and build from scratch. The narrative of this series is strictly documentary. We are separating the proven facts from the romantic myths. There is no need to invoke extraterrestrial intervention or lost continents to explain these achievements. The reality that human beings working with bronze, clay, glass, and water solved problems that we still grapple with today is far more compelling. The intricate gear trains of the Antikythera Mechanism are not evidence of alien contact, they are evidence of human brilliance. The ruby glow of the Lycurgus cup is not magic, it is chemistry. By grounding these discoveries in the hard sciences of physics and engineering, we honour the ancient inventors properly. We acknowledge their labour and their intellect, recognising that they laid the foundations of science long before history gave them credit. Ultimately, this investigation serves as a mirror. By looking at what was lost, we gain a better perspective on what we possess. We see that the line between ancient and modern is thinner than we imagine. The principles governing the automata of Alexandria are the same principles governing the robotics of today. The logic of the Antikythera gears is the ancestor of our own computational logic. We are walking in the footsteps of giants who have been forgotten, exploring a heritage of innovation that was buried by time. This chapter opens the door to that buried world, inviting a re-examination of history, where the ancients are not primitive precursors, but pioneer engineers whose blueprints were simply misplaced in the wreckage of time. In the year 132 AD, the vast territories of the Han dynasty were held together by a fragile philosophical thread known as the Mandate of Heaven. This political and spiritual doctrine asserted that the emperor's right to rule was granted by the cosmos itself, contingent upon his virtue and his ability to maintain harmony between the human and natural worlds. In this highly charged atmosphere, natural disasters were not viewed merely as geological or meteorological accidents. They were interpreted as terrifying celestial reprimands, direct evidence that the emperor was failing in his duties. Earthquakes were particularly feared, as they represented a fundamental disruption of the Earth's stability, often triggering panic, rebellion, and political instability. The imperial court in the capital city of Luoyang lived in a state of constant vigilance, needing to know immediately where and when a disaster had struck, so that aid could be dispatched and order maintained. It was within this cauldron of political pressure and scientific curiosity that Zhang Heng, the chief astrologer and a polymath of immense intellect, unveiled an invention that would not be matched in complexity for nearly 2,000 years. Zhang Heng was a man who straddled the line between the mystical and the mechanical. While his contemporaries looked to the stars for omens, Zhang looked to mathematics and observation. He understood that the tremors shaking the empire were physical phenomena that followed specific rules, even if the underlying geology was not yet understood. To capture these invisible forces, he designed the Hufeng Didong Yi, or the instrument for measuring the seasonal winds and the movements of the Earth. To the casual observer standing in the imperial court, the device looked less like a scientific instrument and more like a masterpiece of bronze artistry. It stood approximately 6 feet in diameter, shaped like a large wine jar or an urn, with a central dome that hid its inner workings from view. The exterior was a testament to the advanced metallurgy of the Han era, cast with intricate reliefs of mountains, tortoises, birds, and beasts, symbolizing the chaotic natural world that the device was meant to tame. The functional interface of the machine was integrated seamlessly into its aesthetic design. 8 bronze dragons were affixed to the outside of the vessel, arranged at equal intervals to represent the 8 principal directions of the compass: north, south, east, west, northeast, northwest, southeast, and southwest. Each dragon head was sculpted with an open mouth, poised as if to roar, and balanced precariously inside each mouth was a small bronze ball. Directly beneath each dragon sat a corresponding bronze toad, its mouth gaping wide open, waiting to catch the ball should it fall. The visual language was clear. The dragon, a symbol of imperial power and celestial force, would communicate with the toad, a creature of the earth, bridging the gap between the heavens and the ground. However, the true genius of the seismoscope lay not in its external ornamentation, but in the invisible mechanism sealed within the bronze casing. Beneath the domed lid, Zhang Heng had constructed a system based on the principle of inertia, a concept that would not be formally codified by Western physics until the time of Galileo and Newton. The core of the device featured a massive central pillar, a heavy pendulum suspended from the top of the vessel. This pendulum was the sensing element, designed to remain stationary due to its own inertia, while the outer casing of the vessel moved in sympathy with the ground during a tremor. When an earthquake occurred, the ground, and the bronze vessel resting upon it, would shift abruptly. The heavy pendulum resisting this movement would appear to swing relative to the vessel's walls. This relative motion was the key to detection. The pendulum was connected to a series of 8 transmitting rods or levers, each linked to the jaw mechanism of one of the 8 dragons on the exterior. The engineering challenge was immense because the device needed to distinguish between the distinct rhythmic waves of a distant earthquake and the chaotic high-frequency vibrations caused by passing carts or people walking nearby. Zhang Heng achieved this through a delicate calibration of the internal trigger system. The mechanism was incredibly sensitive, capable of detecting the primary pressure waves of a seismic event, the P waves, which travel faster than the destructive shear waves and often arrive before any shaking is felt by humans. When the pendulum swung in the direction of the wave's origin, it would push the corresponding lever. This lever would trip a latch, causing the dragon facing the direction of the earthquake to open its mouth. The bronze ball would drop, struck by gravity, and land in the mouth of the toad below. The sound of the ball striking the bronze toad was an essential part of the device's utility. It produced a loud, resonant clang, a metallic alarm that could alert the palace attendants even if they were not looking directly at the machine. This acoustic signal transformed the seismoscope from a passive recording device into an active warning system. Furthermore, the mechanism was designed with a lockout feature. Once one ball had been released, the internal geometry prevented the other dragons from triggering. This ensured that the device indicated the initial direction of the shockwave clearly, rather than releasing multiple balls as the pendulum swung back and forth during the aftershocks or the settling of the mechanism. It provided a single definitive vector of origin. For some time, the officials of the Han court viewed Zhang Heng's invention with a mixture of intrigue and skepticism. It was a beautiful object, certainly, but the idea that a bronze jar could feel the trembling of the earth across hundreds of miles seemed implausible to men accustomed to relying on messengers and signal fires. The true test of the machine came on a quiet afternoon when the court was in session. Without warning, the mechanism activated. The internal pendulum swung, a lever was pressed, and the dragon facing west released its ball. The sharp clang echoed through the hall, drawing the immediate attention of the courtiers. They rushed to the device and saw the bronze ball resting in the mouth of the western toad. Confusion reigned in the capital. The officials and the citizens of Luoyang had felt nothing. The ground beneath their feet was steady. The hanging lamps did not sway. The water in the wells remained calm. To the skeptics, this was proof that Zhang Heng's device was a failure, a toy that had malfunctioned or been triggered by a random vibration. There was talk of the machine being unreliable, perhaps even a fraudulent attempt to gain imperial favour. Zhang Heng, however, stood by the science of his creation. He maintained that an earthquake had indeed occurred to the west, at a distance too great for them to feel, but violent enough for the sensitive inertia of the pendulum to detect. The tension in the court was palpable, as the credibility of the chief astrologer, and by extension, the emperor's ability to perceive the will of heaven, hung in the balance. The vindication arrived several days later, carried by the hooves of exhausted horses. Messengers rode into Luoyang from the Longxi Commandery, a region located hundreds of miles to the west in what is now Gansu province. They brought grim news. A devastating earthquake had struck their region at the exact hour that Zhang Heng's dragon had dropped its ball. The destruction was widespread, with city walls collapsed and landslides blocking the mountain passes. The report confirmed not only the occurrence of the disaster, but also the precise direction indicated by the machine. The skepticism of the court evaporated instantly, replaced by a profound awe for the mechanical prowess that allowed the capital to perceive events far beyond the horizon of human senses. This success fundamentally changed the administrative capacity of the Han government. By knowing the direction of a quake immediately, the emperor could dispatch relief columns, food supplies, and military aid to the affected region days before the official request for help arrived. In an era where travel was limited to the speed of a horse, this head start was invaluable. It allowed the central government to project an image of omniscience and benevolence, reinforcing the political narrative that the emperor was in tune with the natural world. The seismoscope was no longer just a scientific curiosity, it became a vital instrument of statecraft, a technological solution to the logistical nightmare of governing a massive, geologically active empire. The legacy of Zhang Heng's seismoscope extends far beyond its immediate utility in the 2nd century. It represents a pinnacle of ancient engineering that challenges our modern assumptions about the trajectory of scientific progress. The device demonstrated a sophisticated understanding of mechanics, specifically the conversion of small-scale kinetic energy into a mechanical trigger. It utilized the concept of amplification, taking a vibration too subtle for the human inner ear and translating it into a visible and audible signal. Moreover, the manufacturing of the device required a mastery of bronze casting and friction reduction that would be difficult to replicate even today without modern machining tools. The internal components had to be balanced with absolute precision. If the pendulum were too heavy, it would damage the levers. If too light, it would fail to overcome the friction of the latch. Tragically, the physical continuity of this technology was broken. In the centuries following the Han Dynasty, during periods of war and unrest, the original device was lost to history, while historical texts preserved the description of its exterior and the general principle of its operation. The exact internal schematics were forgotten. Later, Chinese dynasties attempted to recreate the device, but many failed to achieve the same level of sensitivity, leading some historians to doubt the accuracy of the original records. It was not until the 20th and 21st centuries that modern seismologists and historians, using computer modelling and advanced reconstructions, proved that Zhang Heng's design was indeed functional. They confirmed that a properly balanced pendulum, interacting with a sensitive trigger mechanism, could detect distant earthquakes exactly as the chronicles described. This artifact serves as a stark reminder of the non-linear nature of technological history. We often assume that knowledge is cumulative, that once a civilization learns to build a computer or a seismograph, that knowledge is permanent. But the silence that followed Zhang Heng's era proves otherwise. Humanity possessed the ability to monitor earthquakes in 132 AD, yet that capability vanished, leaving civilization blind to the tremors of the Earth for nearly 2 millennia until the invention of modern seismographs in Europe. The bronze dragons of Luoyang stand as a testament to a lost golden age of mechanics, where art and science were fused into a single vessel that listened to the heartbeat of the world. The story of the seismoscope is not merely about a clever trick with balls and toads. It is about the application of logic to the terrifying unknown. In a world dominated by superstition, where disaster was seen as the wrath of gods, Zhang Heng chose to treat the Earth as a physical system that could be measured, understood, and eventually managed. He replaced fear with data. This shift in perspective, from mythological interpretation to mechanical observation, is the hallmark of the scientific method. The Hufeng Didong Yi was a beacon of rationality, casting a long shadow forward in time, signalling that the ancients were not stumbling in the dark, but were capable of grasping the subtle physics of the planet long before we gave those forces names. As we move away from the bronze foundries of ancient China, we must carry this realization with us. The ancients were capable of manipulating matter at a level that defies the primitive label. If they could harness the inertia of the Earth to detect invisible waves, what else could they do? The answer lies not in the macrocosm of geology, but in the microcosm of chemistry and light. Our journey now shifts from the heavy, shifting tectonic plates of the East to the delicate, shimmering glassworks of the West, where Roman artisans were unknowingly conducting experiments in nanotechnology that would not be fully understood until the age of the electron microscope. The true test of Zhang Heng's genius lies not in the surviving historical descriptions, but in the rigorous physical reconstructions attempted by modern scientists. For centuries, the specific internal mechanism of the Hufeng Didong Yi was a subject of intense debate because the original device did not survive the tumultuous end of the Han Dynasty. While the history of the later Han provided a tantalizingly brief description of a central pillar capable of moving in 8 directions, it failed to specify exactly how this pillar connected to the dragon jaws. This gap in the historical record forced 20th and 21st century archaeologists and seismologists to engage in a process of reverse engineering that spanned decades. Early attempts in the 19th and mid-20th centuries often relied on the concept of an inverted pendulum, essentially a stick balanced precariously on a base. While this design could indeed fall over when the ground shook, it lacked the stability and selectivity required to distinguish between a distant earthquake and a nearby carriage passing on the road. These early replicas were unstable and prone to false positives, leading many Western critics to dismiss the original accounts as exaggerated folklore or court propaganda. It was not until the early 2000s that a team of seismologists and archaeologists from the Chinese Academy of Sciences, led by Feng Rui, achieved a breakthrough that vindicated Zhang Heng's reputation. They abandoned the unstable inverted pendulum model in favour of a suspended pendulum design, which aligns more accurately with the physics of inertia and the obscure terminology found in ancient texts. In this configuration, a heavy mass hangs from the centre of the vessel's lid. When the ground moves beneath the device, the heavy pendulum tends to remain stationary due to its inertia, while the vessel itself shifts with the Earth. This relative motion allows the pendulum to swing toward the direction of the shockwave. The modern reconstruction team realised that the interface between this swinging pendulum and the trigger mechanism for the dragons required extreme precision. They designed a system of levers and channels where the slightest displacement of the central weight would push a slider, releasing the bronze ball held in the dragon's mouth. To verify this design, the team placed their reconstruction on a modern shake table, a device used by engineers to test the earthquake resistance of buildings. They fed the table historical seismic data, simulating the specific wave patterns of earthquakes that occurred in China and around the world. The results were startling. The replica did not merely react to random shaking, it accurately identified the direction of the longitudinal primary waves, or P waves, which travel faster than the destructive secondary transverse waves. The device proved capable of filtering out high-frequency background noise, such as human footsteps or wind, and responding only to the low-frequency, long-period waves characteristic of distant seismic events. This experimental verification proved that the mechanics described in the 2nd century were not only plausible, but highly sophisticated. The system acted as a mechanical filter, a feat of engineering that predates modern signal processing by nearly 2,000 years. Comparing the Hufeng Didong Yi to contemporary seismological instruments reveals both the limitations and the brilliance of the ancient design. Modern seismometers are electromechanical devices that continuously record ground motion in 3 dimensions: vertical, north-south, and east-west, producing a seismogram that details the magnitude, duration, and frequency of the tremors. Zhang Heng's device was technically a seismoscope, not a seismograph, as it did not record the waveform or the time of the event. It was a binary directional alarm. Once a ball dropped, the device was triggered and could not record subsequent shocks until it was manually reset. It offered no information regarding the depth of the hypercenter or the magnitude of the energy release on the Richter scale. However, considering the context of 132 AD, the comparison should not be framed by what the device lacked, but by the specific problem it solved. The primary need of the Han administration was not scientific analysis of wave propagation, but rapid administrative response. In this regard, the Seismoscope was perfectly optimized for its user. It functioned as a directional trigger for state intervention, offering a clear, unambiguous signal that required no specialized training to interpret. If the Western Dragon dropped a ball, the disaster was in the West. The precision of Zhang Heng's design becomes even more impressive when analyzing the historical record of its most famous validation. In 138 AD, the device in the capital city of Luoyang triggered, releasing a ball from the Western Dragon. The mechanism clashed loudly, alerting the court attendants. However, no one in the capital had felt any tremors. The ground beneath their feet seemed perfectly still, and the political enemies of Zhang Heng seized the opportunity to ridicule the invention. They argued that the device had failed, triggered perhaps by an internal imbalance or a gust of wind, and that the chief astrologer was peddling deceit. For several days, the skepticism in the court grew, threatening Zhang Heng's position and the credibility of his scientific approach. The tension between empirical observation and human sensory perception was palpable. The machine claimed a reality that the humans could not verify. Redemption arrived days later in the form of a weary messenger riding fast from the Longji commandery, located far to the west of the capital. The messenger reported a devastating earthquake that had struck the region at the exact time the seismoscope had triggered. The distance between Luoyang and the epicenter was roughly 400 miles, a range that naturally dampened the shockwaves before they reached the capital, making them imperceptible to human senses but distinct enough for the sensitive pendulum of the bronze vessel. This event is cited by historians as the definitive proof of the device's functionality. It demonstrated that the instrument possessed a threshold of sensitivity superior to the human body, effectively extending the sensory range of the state. The arrival of the messenger silenced the critics and established the seismoscope as a vital tool for imperial governance. It was the first time in history that a machine had successfully proven a physical phenomenon occurred beyond the horizon, independent of human witness at the observation site. The impact of this successful test on early warning systems and disaster response in ancient China was profound. In the vast territory of the Han Empire, communication was limited to the speed of a horse. If a remote province was struck by an earthquake, local officials might take days or weeks to assess the damage and dispatch a request for aid. By the time the news reached the capital, the window for effective relief might have closed, leading to famine, unrest, and potential rebellion. The seismoscope short-circuited this delay. By indicating the direction of the quake immediately, the central government could mobilize grain convoys, medical aid, and military support toward the affected region before the official report even arrived. This proactive capability was crucial for maintaining the mandate of heaven. The emperor's legitimacy rested on his ability to harmonize the human and natural worlds. Rapid response to natural disasters was interpreted as competence and moral rectitude. Furthermore, the data collected by the seismoscope allowed the Han court to maintain a centralized record of seismic activity, contributing to a bureaucratic understanding of the empire's geography. It shifted the perception of earthquakes from purely supernatural punishments to observable, trackable events. While the spiritual interpretation remained dominant in the culture, the operational response became increasingly logistical. The device essentially functioned as a node in a proto-information network, where the bronze vessel acted as the receiver and the seismic waves as the transmission signal. It was a singular point of high-tech monitoring in an agrarian society, a capability that would not be replicated until the development of telegraphy and modern seismology in the 19th century. The limitations of the device, however, eventually contributed to its disappearance. Because the mechanism required precise calibration and maintenance, it was vulnerable to neglect. When the Han dynasty collapsed into the chaos of the Three Kingdoms period, the institutional knowledge required to build and maintain such delicate instruments was lost. The bronze vessels were likely melted down for coinage or weapons, and the intricate internal levers rotted or corroded. Unlike a plough or a water wheel, the seismoscope was not a tool of production, but a tool of observation, making it less essential for immediate survival during times of war. The technology was a luxury of a stable, centralized state. Without the support of a wealthy imperial court dedicated to astronomical and geological study, the science of seismoscopy withered. Modern analysis of the Longxi event using the 2005 reconstruction has provided further insights into the specific geological conditions that allowed the device to work. Seismologists suggest that the sediment-filled basin of Luoyang may have amplified the long-period waves arriving from the west, a phenomenon known as site amplification. This would explain why the pendulum inside the vessel could swing with enough force to dislodge the ball, while the people standing nearby felt nothing. The resonance frequency of the pendulum likely matched the frequency of the seismic waves travelling through the soft soil of the Yellow River Valley. This implies that Zhang Heng, whether by intuition or trial and error, had tuned his device to the specific acoustic properties of the local geology. It was not a generic instrument, but one calibrated for its environment. The verification of the seismoscope serves as a powerful corrective to the narrative of technological evolution. It proves that the path to modern science is not a straight line, but a series of loops and dead ends. The Han dynasty possessed a capability that the rest of the world would not achieve for nearly 2 millennia. The reconstruction of the device confirms that the principles of inertia and resonance were being practically applied to solve complex problems long before Galileo or Newton formulated the laws of motion. The bronze dragons were not merely decorative art, They were the visible components of a rigorous mechanical logic. This machine stood at the intersection of geology, physics, and public administration, embodying a holistic approach to science that integrated observation with governance. As we analyse the success of the Seismoscope, we are forced to confront the fragility of such knowledge. The device worked, it saved lives, it strengthened the state, yet it vanished. The physical reality of the Seismoscope challenges us to look for other lost technologies that may have existed in the blind spots of history. It prepares us to accept that ancient engineering was capable of manipulating the material world in ways that we're only just beginning to rediscover. This acceptance is crucial as we turn our gaze from the macromechanics of earthquakes to the microengineering of light and colour. The same intellectual curiosity that drove Zhang Heng to measure the Earth drove Roman artisans to manipulate the very structure of matter, leading to the creation of the Lycurgus cup, an artifact that proves the ancients were masters of more than just bronze and stone. The artifact sits in the British Museum, unassuming at first glance, appearing as a dull, pea-green chalice adorned with intricate relief carvings. To the casual observer walking past the display case, it looks like a piece of opaque jade or perhaps a weathered serpentine stone, typical of the luxury goods produced during the late Roman Empire. However, when light is removed from the front of the object and shone through it from behind, the dull green evaporates instantly, replaced by a glowing, translucent ruby red. This radical transformation, known as dichroism, is not a trick of modern lighting or a result of fading paint, but a fundamental property of the glass itself. For decades after its acquisition in the 1950s, this optical behaviour baffled curators and scientists alike, representing a level of material science that seemed impossible for the 4th century AD. The cup is a cage cup, or diatretum, the most complex and difficult type of Roman glass to manufacture. Unlike blown glass, or simple mould-pressed vessels, a cage cup is created by cutting and grinding away the background of a thick blank of glass until the figures stand in high relief, connected to the inner beaker only by thin, hidden bridges of glass. The craftsmanship required to execute such a design is staggering, as the vibrations from the cutting wheel alone could shatter the delicate mesh of vines and figures. The scene depicts the Thracian king Lycurgus, a mythological figure who made the fatal mistake of banning the worship of Dionysus and attacking the god's followers. In the relief, Lycurgus is shown entangled in grapevines, his body contorted in panic as he is strangled by the very plants he sought to destroy. The artistic execution is masterful, but it is the chemistry of the glass, rather than the artistry of the cut, that secures the cup's place in the history of science. For years, the mechanism behind the colour shift remained a matter of speculation. Early theories suggested that the glass might contain rare earth elements, or that the effect was achieved through layers of different coloured glass fused together. It was not until 1990 when researchers placed tiny fragments of the glass under a transmission electron microscope that the true cause was revealed. The glass contains gold and silver, but not in the form of foil or leaf. The metals are present as nanoparticles, ground so finely that they are invisible to the naked eye. These particles are approximately 50 to 70 nanometers in diameter. To put this in perspective, a single grain of salt is 1,000 times larger. This specific size is not arbitrary. It is the precise dimension required to interact with light waves in a way that produces the dichroic effect. The physics at play here involves a phenomenon known as surface plasmon resonance. When light hits the metallic nanoparticles, the electrons on the surface of the metal vibrate. The gold particles absorb light at the blue and green end of the spectrum, while the silver particles influence the yellow tones. When light reflects off the front of the cup, the scattering effect makes the glass appear green, imitating the look of jade. However, when light passes through the glass, the specific absorption properties of the gold-silver alloy allow only the red spectrum to transmit, causing the cup to glow with the colour of deep wine. This is the same principle used in modern medical diagnostics and optical sensors, yet it was effectively utilised by Roman workshops 1600 years ago. The consistency of the nanoparticle distribution challenges the notion that this was a happy accident. Analysing the chemical composition reveals a precise ratio of 3 parts, silver to 1 part gold, with trace amounts of copper and manganese likely added to facilitate the melting process or tune the colour. The particles are dispersed uniformly throughout the glass matrix, preventing them from clumping together. which would destroy the optical effect and result in a muddy brownish glass. Achieving this uniformity required a mastery of colloidal chemistry that historians did not believe existed in the ancient world. The Roman artisans likely ground the gold and silver into a fine dust, perhaps mixing it with antimony or other salts, to create a suspension that could be added to the molten glass. This process, repeated with exacting standards, constitutes an early form of nanotechnology. The implications of this manufacturing process are profound when considering the Roman glass industry as a whole. Glassmaking in Rome was a massive industrial enterprise, with primary workshops in Egypt and the Levant producing raw glass ingots that were shipped across the empire to be remelted and shaped. The Lycurgus cup, however, represents a specialized boutique production. The control required to keep the metal particles at the 50 nanometer scale suggests that the makers understood the relationship between the additive and the resulting color, even if they did not understand the subatomic physics. They knew that if they added the metal dust in a specific way, the glass would change color. If the particles had been slightly larger, the glass would have been opaque, slightly smaller, and the color would have been faint or non-existent. Scholars continue to debate whether the Lycurgus cup is a singular anomaly or the survivor of a wider class of dichroic vessels. A few other fragments of Roman glass show similar properties, but none possess the dramatic clarity and intense color shift of this cup. This scarcity suggests that the technique was either a closely guarded trade secret held by a single workshop or a notoriously difficult process with a high failure rate. It is easy to imagine a workshop floor littered with failed attempts, glass that turned brown, grey, or remained stubbornly clear before the masters perfected the ratio. The existence of the cup proves that the methodology existed, but its rarity indicates that the knowledge was fragile, likely dying out with the specific artisans who held the recipe. The cultural context of the cup adds a layer of grim irony to its function. The vessel was designed to hold wine. When empty, the cup is green, the colour of unripened grapes or the vines that entrap the king. When filled with red wine and lit from within, perhaps by the flickering light of an oil lamp at a dinner party, the cup would turn red. This transformation would visually enact the myth. As the drinker consumed the wine, the red glow would simulate the blood of the king or the power of Dionysus, completing the narrative arc through the act of drinking. The technology was not just for show, it was integrated into the storytelling function of the object. The optical engineering served the mythology, creating a dynamic user experience that static sculpture could not achieve. This integration of narrative and material science highlights the sophistication of the Roman elite's dining culture. These were not primitive people drinking from clay pots. They were connoisseurs who appreciated the interplay of light, liquid, and story. The cup would have been a conversation starter, a status symbol that demonstrated the owner's access to the rarest craftsmanship in the empire. It reflects a society that valued technical innovation when it could be applied to luxury and aesthetic pleasure. While Zhang used his engineering genius to serve the state through earthquake detection, the makers of the Lycurgus cup applied similar levels of precision to the service of leisure and art. The manufacturing technique likely involved the use of a colloidal gold solution, a method that would not be scientifically described until Michael Faraday studied it in the 19th century. The Romans effectively bypassed 1,500 years of chemical development through empirical trial and error. They discovered that adding gold to glass produced red, a counterintuitive fact since gold is yellow. This alchemical transformation, turning yellow metal into red glass, was likely viewed with a sense of wonder bordering on magic. Yet, the reliability of the chemistry proves it was technology, not magic. The artisans were manipulating matter at the molecular level, controlling the cooling rates and the chemical environment of the furnace to prevent the metals from oxidizing or precipitating out of the solution. The survival of the Lycurgus cup is miraculous in itself. Most Roman cage cups were found in graves, protected by the earth, but the Lycurgus cup has a history of being above ground, passing through the hands of the Catholic Church and various noble collections before reaching the museum. Its rim was later mounted with a gilt bronze collar in the 18th or 19th century, obscuring the original glass edge, but the main body of the vessel remains intact. This continuity of ownership suggests that the colour-changing property was recognised and valued throughout the centuries, even if the reason for it was forgotten. It became a curiosity, a relic of a lost age of giants who knew how to trap light inside stone. Studying the Lycurgus cup forces a re-evaluation of the timeline of materials science. We often associate nanotechnology with sterile modern laboratories, silicon chips, and electron microscopes. To find it embedded in a decorative wine cup from the 4th century disrupts the linear narrative of progress. It demonstrates that advanced capability does not always require advanced theory. The Roman glassmakers did not need to know about surface plasmon resonance to utilize it. They only needed to know the recipe. This distinction between theoretical knowledge and practical application is crucial. A civilization can possess the how without the why, allowing them to build devices that future generations, who have lost the how, will struggle to explain even with their superior theoretical understanding. The mystery of the Lycurgus cup is solved, but the wonder remains. The solution, gold and silver nanoparticles, is just as impressive as the mystery itself. It confirms that the ancient world was not merely a time of stone and bronze, but a period of complex chemical experimentation. The artisans who ground the gold for this cup were pioneers of optics, creating a device that manipulated the visible spectrum to tell a story of divine punishment. As we move from the static mastery of Roman glass to the active chemical energy of the Baghdad Battery, we see a shift from manipulating light to manipulating the flow of electrons themselves, further proving that the foundations of modern physics were being laid in the workshops of antiquity. When scientists finally placed a fragment of the Lycurgus cup under a transmission electron microscope in 1990, the mystery of its colour-shifting glass was stripped of its mythology and reduced to hard data. For decades, the scientific community had debated the source of the vessel's dichroism, speculating about various chemical oxides or rare earth elements that might cause the glass to appear pea-green in reflected light, yet ruby-red when illuminated from behind. The answer provided by the electron microscope was far more startling than any chemical dye. Embedded within the silica matrix were millions of metallic crystals, invisible to the naked eye and undetectable by standard optical magnification. The British Museum researchers discovered that the Roman artisans had not merely stained the glass, they had engineered it at the atomic level. The glass was impregnated with an alloy of gold and silver, ground down to a scale so minute that it ceases to behave like bulk metal and begins to obey the strange laws of quantum physics. The particles identified by the electron beam measured approximately 50 to 70 nanometers in diameter. To visualize this scale, one must understand that a single nanometer is to a meter what a marble is to the Earth. These particles are roughly 1,000 times smaller than a grain of table salt. At this size, gold no longer shimmers with its characteristic yellow luster. The physics of the material changes entirely because the particle is smaller than the wavelength of visible light. This is the realm of nanotechnology, a field we arrogantly assume to be the exclusive province of the 21st century, yet here it was, suspended in a Roman chalice carved 1600 years ago. The analysis revealed a precise elemental composition. The nanoparticles were an alloy consisting of approximately 70% silver and 30% gold, with trace amounts of copper. This specific ratio was not accidental debris from a dirty workshop floor. It was a critical component of the optical effect. The mechanism driving this colour change is a phenomenon known to modern physicists as surface plasmon resonance. In a bulk piece of metal, like a gold coin or a silver spoon, the electrons are free to move across the surface, forming a sea of negative charge. When light hits this surface, the electrons vibrate and reflect the light, creating the shiny appearance we associate with polished metal. However, when the metal is reduced to a nanoparticle, the rules of engagement change. The particle is so small that the electron cloud is confined. When light waves strike these confined electrons, they cause the cloud to oscillate back and forth in a synchronized rhythm. This oscillation is the resonance. In the case of the Lycurgus cup, the specific size of the particles and the specific gold-silver alloy created a resonance frequency that matched the blue and green spectrum of visible light. When white light attempts to pass through the glass, the nanoparticles absorb the blue and green wavelengths, energizing their electron clouds. The red wavelengths, however, are too long to be absorbed by this specific resonance. They pass through the glass unimpeded. Consequently, when a viewer looks through the cup, the only light that reaches their eye is the red spectrum, giving the vessel its glowing, blood-like translucence. Conversely, when light bounces off the front of the cup, the scattering effect dominates. the larger silver component in the alloy contributes to scattering the green wavelengths back toward the viewer, creating the opaque, jade-like appearance. The Roman craftsmen had effectively built a photonic filter that manipulated the electromagnetic spectrum centuries before Newton ever passed light through a prism. The precision required to achieve this effect is staggering. The concentration of gold in the Lycurgus glass is extremely low, roughly 40 parts per million. If the particles had been slightly larger, the glass would simply look murky or muddy. If they were smaller, the colour absorption would shift, perhaps turning the glass violet or yellow instead of the dramatic ruby red. The uniformity of the particle distribution is what separates a failed experiment from a masterpiece. In modern laboratories, creating a uniform dispersion of nanoparticles requires centrifuges, lasers, and sterile environments to prevent the particles from clumping together. The Romans achieved this inside a wood-fired furnace, using nothing but bellows, clay pots, and empirical intuition. This leads to the inevitable question of the manufacturing process. How did Roman glassmakers, lacking any concept of atoms or wavelengths, execute a protocol of such chemical delicacy? It is unlikely they were grinding gold down to the nanometer scale mechanically, as that is physically impossible with ancient tools. Instead, they were likely utilizing a form of high-temperature chemistry that anticipated the purple of Cassius, a pigment production method not formally discovered until the 17th century. The process would have involved dissolving gold and silver into the molten glass mixture, perhaps by adding coins or gold leaf along with antimony and other reducing agents. The critical step was likely the heat treatment, or striking of the glass. When the gold and silver are first dissolved in the silica melt, they exist as individual atoms or ions, colourless and invisible. The glass at this stage would appear clear. To create the nanoparticles, the glass makers had to reheat the finished glass to a specific temperature for a specific duration. This annealing process allowed the metal atoms to migrate through the hot, viscous glass and clump together. As they collided, they formed tiny crystals. The skill of the master craftsman lay in knowing exactly when to stop the heating. Stop too soon, and the particles are too small to affect the light. Heat it too long, and the particles grow too large, ruining the transparency. The Roman artisan was controlling the growth of crystals at the nanoscale by eye, judging the readiness of the material by the subtle shifts in hue as the glass cooled. The presence of trace elements like antimony and copper suggests a sophisticated understanding of redox reactions, reduction, and oxidation. Antimony acts as a reducing agent, helping to strip the oxygen from the metal ions and allowing them to revert to their metallic state, which is necessary for the plasmonic effect. Without this chemical trigger, the gold would remain dissolved as an ion, and the glass would remain colourless. This implies that the recipe for the Lycurgus glass was a complex chemical system, involving multiple ingredients that had to be balanced perfectly. It was not enough to just throw gold into the pot. One had to create the chemical environment in which gold would precipitate out of the solution in a controlled manner. Comparing this ancient technique to modern nanofabrication highlights both the ingenuity of the past and the circular nature of discovery. Today we use gold nanoparticles for very similar optical properties in medical diagnostics. The red line on a home pregnancy test or a COVID-19 rapid antigen test is caused by the same phenomenon found in the Lycurgus cup. These tests use gold nanoparticles that are chemically treated to bind to specific biological markers. When they congregate in a line, their collective surface plasmon resonance absorbs green light and reflects red, creating the visible indicator. In a sense, the Lycurgus cup is a massive vitrified biosensor, although it detects light rather than proteins. Furthermore, the field of plasmonics is currently revolutionizing information technology and solar energy. Engineers are designing dichroic glass for skyscrapers that can filter out heat-generating infrared light while letting in visible light, reducing cooling costs. They are building optical circuits that use light instead of electricity to process data, relying on the same electron oscillations that turn the Roman cup red. The Lycurgus cup is essentially a photonic crystal, a material structured to affect the motion of photons. The difference is that modern engineers design these structures using supercomputers and fabricate them with ion beams, while the Romans did it with fire and sand. The existence of this technology in the 4th century challenges our linear view of scientific history. We often assume that technology evolves in a straight line from simple to complex, but the Lycurgus cup represents a spike on the graph, a peak of capability that was reached and then lost. the knowledge of how to create dichroic glass of this quality evaporated with the collapse of the Roman industrial networks. While red glass existed in the medieval period, the specific ruby gold glass that relied on this precise nanoparticle suspension did not reappear in the West until the 17th century. For over a millennium, humanity possessed the physical artifact of the cup but lost the intellectual software required to replicate it. The analysis of the glass composition also reveals the economic and logistical power of the Roman Empire. The raw materials required for this chemistry, gold, silver, antimony, high-quality silica, and the fuel for the furnaces, were sourced from different corners of the known world. The ability to bring these materials together and afford the waste inherent in such an experimental process speaks to a society with significant surplus wealth and a specialized class of artisans supported by elite patronage. Nanotechnology, in this context, was a luxury good. It was the ultimate display of power, the ability to command nature to show a different face depending on how one looked at it. Scientific examination has also ruled out the possibility that the Lycurgus cup was a singular freak accident. While rare, fragments of other Roman dichroic glass have been found, though none as complete or as intricate as the cup. This confirms that the production of nanoparticle glass was a known, albeit exclusive, industrial process. There were likely workshops in Rome or Alexandria that held the secret recipe, passing it down through apprenticeships until the chain was broken by war, plague, or economic collapse. The consistency of the particle size across the vessel, varying only by a few nanometers, suggests a standardized production method, not a random fluke of the furnace. The study of the Lycurgus cup serves as a humbling reminder to the modern material scientist. We pride ourselves on our ability to manipulate matter atom by atom, yet we are looking at a device that performs the same function, built by people who thought the sun was a chariot. The Roman understanding of surface plasmon resonance was practical rather than theoretical. They knew that it worked, even if they didn't know why. But in the history of technology, the that often precedes the why by centuries. The steam engine was invented before the laws of thermodynamics were written. Aspirin was used before we understood neurochemistry. The Lycurgus cup proves that nanotechnology is no different. It is not a modern invention, but a fundamental property of matter that humans have been tinkering with for thousands of years, occasionally stumbling upon the sublime. The investigation into the Lycurgus cup concludes not with a dismissal of ancient myths, but with a validation of ancient competence. The magic of the cup was real, but it was the magic of physics, harnessed by artisans who pushed the boundaries of their materials to the absolute limit. They froze a specific moment of chemical transition in glass, locking millions of gold atoms in a permanent state of resonance. As we turn our attention from the manipulation of light in Rome to the manipulation of electricity in the deserts of Mesopotamia, we find that the ancients were not just building static monuments. They were experimenting with the fundamental forces of the universe, creating devices that, like the Lycurgus cup, still have the power to illuminate the dark corners of history. In 1938, the German archaeologist Wilhelm König found himself wandering the archives of the National Museum of Iraq, a repository of history that held the accumulated debris of millennia. Among the grandiose statues of Assyrian kings and the intricate cuneiform tablets of Sumerian bureaucrats, König stumbled upon a collection of artifacts that seemed entirely unremarkable at first glance. They were simple, yellow clay jars, roughly the size of a human fist, standing about 14 centimeters tall. They lacked the artistic flair of the Lycurgus cup or the mechanical complexity of the Antikythera Mechanism. To the untrained eye, they were merely storage vessels, perhaps for oils or cosmetics, discarded in the ruins of Kujut Rabu, a site near Baghdad. However, König was struck by the peculiar internal arrangement of these vessels, a configuration that defied the logic of simple storage and hinted at a purpose that history books claimed was impossible for the time period. The anatomy of the device was specific and deliberate, suggesting a blueprint rather than a happy accident. Inside the ceramic jar sat a cylinder made of rolled copper sheet, soldered with a 60-40 lead-tin alloy, a ratio comparable to the solder used in modern electronics. Suspended inside this copper cylinder, but carefully prevented from touching it, was an iron rod. The top of the jar was sealed with bitumen, a natural asphalt common in the region, which held the iron rod in place and acted as a lid. This use of bitumen was the critical detail that shifted the object from a container to a mechanism. Bitumen is an electrical insulator. If the purpose of the jar were merely to hold a scroll or seeds, a simple clay or wooden stopper would have sufficed. The deliberate separation of the iron from the copper and the insulation of the entire assembly mirrored the fundamental architecture of a galvanic cell. When Koenig published his findings, he proposed a theory that sent shockwaves through the archaeological and scientific communities. These clay pots were electric batteries. The implication was staggering because it disrupted the accepted timeline of scientific discovery by nearly 2,000 years. The invention of the battery is traditionally credited to the Italian physicist Alessandro Volta in 1800, who stacked zinc and copper discs separated by brine-soaked cloth to create a continuous flow of charge. Yet here in the dust of the Parthian or Sassanid periods, empires that ruled Mesopotamia roughly between 250 BC and 250 AD, was an artifact that appeared to utilize the exact same principles of electrochemistry. The existence of the Baghdad Battery suggested that the manipulation of electron flow was not a product of the European Enlightenment, but a practical technology known to the artisans of the ancient Near East. To understand how such a device could function, one must look at the chemistry of the components found within the jar. The copper cylinder acted as the cathode, while the iron rod served as the anode. For the battery to generate power, it required only one missing ingredient, an electrolyte solution. While the original liquid had long since evaporated, the interior of the copper cylinders showed signs of corrosion consistent with the presence of an acidic agent. In the context of ancient Mesopotamia, this would likely have been grape juice, wine, or vinegar. When an acidic liquid fills the jar, it facilitates a chemical reaction where the iron oxidizes, releasing electrons that flow through the electrolyte to the copper. This potential difference creates a voltage. It is a simple, robust chemical engine requiring no theoretical knowledge of atomic structure, only the empirical observation that certain metals, when bathed in acid, produce a force. Following the initial discovery, scientists and engineers constructed replicas to test the viability of Koenig's hypothesis. The results were consistent and undeniable. When filled with vinegar or lemon juice, a single replica of the Baghdad Battery produced a voltage ranging between 0.5 volt and 2 volts. The current was weak, certainly insufficient to power the modern world, but it proved that the device was functionally capable of generating electricity. The physics held up. The question then shifted from could it work to did they know it worked, and more importantly, what was it for? In a world without light bulbs, motors or telegraphs, the utility of a 1-volt battery is not immediately obvious to the modern mind, which associates electricity primarily with illumination and communication. The search for a practical application led researchers to the workshops of ancient jewelers. The most compelling theory for the use of the Baghdad Battery is electroplating, a process used to deposit a thin layer of precious metal, such as gold or silver, onto a base metal like copper. Traditionally, ancient gilding was achieved through a process known as mercury gilding or fire gilding. This involved mixing gold with mercury to create a paste, applying it to the object, and then heating it to burn off the mercury, leaving the gold behind. While effective, this process was incredibly toxic, often poisoning the artisans with mercury fumes. Electroplating, by contrast, creates a cleaner, more uniform layer of gold and requires a steady, low-voltage current, exactly what the battery provided. Experiments conducted by researchers demonstrated that connecting several of these clay jars in a series could generate enough voltage to electroplate small tokens and statuettes. This theory aligns with the archaeological record, which contains numerous examples of Parthian and Sassanid jewellery exhibiting incredibly thin, uniform layers of gold that are difficult to explain through mechanical beating or fire gilding alone. If the battery was indeed a tool of the trade, it would explain why the technology was not widespread or recorded in great public texts. It would have been a trade secret, a proprietary method guarded by a specific guild of smiths who could produce magical golden objects without the deadly smoke of mercury. The knowledge would have been passed down orally from master to apprentice, hidden within the confines of the workshop, until the chain of transmission was broken by war or social collapse. However, the electroplating theory is not the only explanation, and the scientific community remains divided. Another school of thought suggests a more mystical application. In the ancient world, the temple was often a place of theatre as much as theology. Priests utilised mechanical automata, optical illusions, and chemical reactions to demonstrate the power of the gods. A bank of these batteries, hidden inside a statue or an altar, could be connected to a metal surface. A worshipper touching the idol would receive a mild but surprising electric shock, a tangible manifestation of the deity's presence. In this context, the battery was not an industrial tool but a device of religious technology, designed to evoke awe and ensure obedience. The sensation of electricity, unknown and invisible, would have been interpreted as supernatural energy, the literal spark of the divine. Despite the allure of the battery theory, skepticism remains a necessary part of the archaeological process. Critics point out that no wires were found with the jars. Iron and copper wires would have corroded away centuries ago, but the lack of physical evidence for a connecting mechanism is a gap in the narrative. Furthermore, the shape of the jars is similar to storage vessels found at nearby Seleucia, which were used to hold papyrus scrolls. The metal rod could have been a spindle around which the scroll was wrapped, and the copper cylinder a protective casing to keep the fragile paper safe from moisture and pests. This scroll theory offers a mundane explanation that requires no leap in technological capability. Yet, it fails to adequately explain the use of bitumen to seal the cap so thoroughly, or why expensive copper and iron were used for storage when clay or wood was abundant. The scroll theory also struggles to account for the galvanic corrosion found inside the cylinders, which strongly implies the presence of a liquid electrolyte rather than dry paper. The debate over the Baghdad Battery highlights a fundamental issue in the study of ancient technology: the distinction between theoretical science and empirical engineering. It is highly unlikely that the Parthians understood the concept of electrons, ions, or voltage potential. They did not have a periodic table or a model of the atom, but the history of invention is often the history of tinkering. It is entirely plausible that an alchemist or metalworker, experimenting with different vessels and fluids for cleaning or dyeing metals, stumbled upon the tingle of electric current. They observed a cause and effect, put these metals in this sour liquid, and a force is generated. They did not need to understand the why to exploit the how. This type of out-of-place artifact forces a re-evaluation of the linear progression of history. We tend to view technological progress as a ladder, with each rung leading inevitably to the next. We assume that electricity belongs to the 19th century, just as we assume steam power belongs to the 18th. But the Baghdad Battery, like the Aeolipile or the Antikythera Mechanism, suggests that the path of knowledge is jagged. Inventions appear, are used for specific purposes, and then vanish when the civilization that supported them collapses. The batteries of Kujut Rabu may have been commonplace in the workshops of the Sassanid Empire, a standard tool for gilding jewellery, only to be discarded and forgotten when the trade routes shifted or the cities burned. The physical reality of the artifacts remains the strongest argument against their dismissal. The specific combination of iron, copper, and an electrolyte is not a random assortment of materials, it is the fundamental recipe for a battery. The probability of these materials coming together in this precise configuration by accident is astronomically low. Whether used for plating gold onto silver, healing pain through primitive electrotherapy, a practice documented in later eras using electric fish, or delivering shocks to the faithful, the device worked. It generated a current. The laws of physics do not change over time. A galvanic cell in 250 BC functions exactly as it does today. Ultimately, the Baghdad Battery serves as a testament to the ingenuity of ancient craftspeople. It reveals a world where the boundaries of what was possible were being pushed through trial and error. It strips away the modern arrogance that assumes we are the first to harness the fundamental forces of nature. Standing in the museum, looking at the corroded iron rod and the dull copper cylinder, one is looking at a ghost of a technology that could have sparked an electrical revolution 2,000 years early, had the social and economic conditions allowed it to flourish. Instead, it remained a curiosity, a singular solution to a specific problem, buried in the sands of Mesopotamia, until a German archaeologist brushed away the dirt and asked a question that we are still trying to answer. The jar sits silent now, its electrolyte long gone, but the potential it represents, the capacity of the human mind to unlock nature's secrets with nothing but clay, metal, and acid, remains as charged as ever. The mechanism inside the clay jar relies on a universal constant of chemistry known as the galvanic principle. At its core, the Baghdad Battery is a device designed to manipulate the flow of electrons between two different metals submerged in an acidic solution. When the iron rod is placed inside the copper cylinder without touching it, and both are immersed in an electrolyte, a chemical reaction is triggered on the surface of the metals. The iron, acting as the anode, has a natural tendency to lose electrons when exposed to acid. These electrons accumulate and create an electrical pressure, or voltage, relative to the copper cylinder, which acts as the cathode. In a modern physics classroom, this is a standard demonstration of a reduction-oxidation reaction, but in the context of the Parthian or Sassanid empires, it represents the harnessing of an invisible force. The device does not store electricity like a capacitor, it generates it through the chemical sacrifice of the iron rod. As the battery operates, the iron corrodes, slowly dissolving into the solution to fuel the movement of the current. Experimental reconstructions of the device have been instrumental in moving the artifact from the realm of speculation to the solid ground of engineering. Since the initial discovery by Wilhelm König, numerous engineers, historians and physicists have built exact replicas using materials that would have been available in Mesopotamia 2,000 years ago. These experiments typically begin by shaping a sheet of copper into a cylinder, soldering the seam with a lead-tin alloy, a technique well within the capabilities of ancient metalworkers. An iron rod is suspended in the centre, held in place by an asphalt stopper that insulates the two metals from one another. This insulation is critical. If the iron touches the copper directly, the circuit shorts and the chemical energy is dissipated as heat, rather than electrical current. The presence of bitumen residues in the original artifacts is the strongest structural evidence that the jars were intended to hold liquid, and that the separation of the metals was deliberate and functional. When these replicas are filled with an electrolyte, the results are immediate and measurable. In tests conducted by researchers at Smith College, as well as in popular demonstrations like those filmed for television documentaries, the single jar consistently produces a voltage reading. Depending on the acidity of the liquid used, a single Baghdad battery generates between 0.5 and 1.1 volts. While this voltage is low by modern standards, less than a standard AA battery, it is undeniable proof of functionality. The current or amperage is generally low, often measured in milliamperes, due to the high internal resistance of the cell. The distance between the iron and the copper, along with the specific conductivity of the liquid, limits how fast the electrons can flow. However, when multiple replicas are connected in series, wiring the iron of one jar to the copper of the next, the voltage adds up. A chain of 10 such jars creates a substantial power source, capable of tasks far more complex than a single cell could achieve. The fuel for this chemical engine was likely a common household liquid. The ancient engineers did not have access to the refined sulfuric or hydrochloric acids used in modern industrial batteries, but they had an abundance of organic acids. The primary candidate is vinegar, or acetic acid, produced through the fermentation of wine. Wine vinegar was a staple of the ancient diet and a common reagent in early chemical processing. Experimental archaeology has shown that grape juice, lemon juice, or even spoiled wine functions effectively as an electrolyte. The acidity provides the hydrogen ions necessary to facilitate the transfer of charge. When vinegar is poured into the replica, the reaction begins almost instantly. Bubbles of hydrogen gas form on the copper cylinder, a byproduct of the chemical exchange, and the iron rod begins to darken as it oxidizes. The simplicity of the fuel source suggests that the battery was not a rare, one-time creation, but a sustainable device that could be recharged simply by replacing the iron rod and pouring in fresh vinegar. The question of efficiency relies on understanding the intended application of the current. For the purpose of lighting a filament bulb, the Baghdad battery is woefully inefficient. It lacks the sustained power output to heat a tungsten wire to incandescence. However, for the process of electroplating, efficiency is measured differently. Electroplating, the process of using electric current to dissolve a thin layer of gold and deposit it onto a base metal like silver or copper, requires a low, steady voltage. In fact, high voltage can burn the plating, resulting in a rough black finish. The 0.5 to 1 volt generated by a single Baghdad battery is theoretically ideal for this delicate chemical work. In laboratory recreations, connecting a replica battery to a gold salt solution resulted in a thin, uniform layer of gold depositing onto a target object over the course of several hours. This suggests that the inefficiency of the battery in modern terms might have been a perfectly tuned feature for its specific ancient application. Comparing this ancient apparatus to modern battery technology reveals both stark differences and surprising similarities, A modern alkaline battery works on the exact same principle. A cathode, manganese dioxide, an anode, zinc, and an electrolyte, potassium hydroxide, interact to push electrons through a circuit. The chemistry has been refined, the materials pioneered for maximum energy density, and the liquid electrolyte replaced with a paste to prevent spilling, but the fundamental physics remain unchanged. The Baghdad Battery is essentially a wet cell, a primitive ancestor of the Daniell cell or the voltaic pile that would be invented in Europe in the 19th century. Alessandro Volta's invention, which is credited with starting the electrical age, consisted of stacked discs of zinc and copper separated by brine-soaked cloth. Structurally, the Baghdad Battery is simply a different geometric configuration of the same components. A cylinder instead of a disc, a jar instead of a stack. The disparity lies in the optimization and the theoretical understanding. Modern batteries are engineered to minimize internal resistance and maximize shelf life. The Baghdad Battery, with its wide gap between the iron and copper and its weak organic electrolyte, suffers from significant energy loss. The iron rod would degrade even when the battery was not in use if left in the acid, a problem modern engineering solves with separators and inhibitors. Furthermore, there is no evidence that the ancient artisans understood the concept of voltage, or amperage, as mathematical quantities. They were likely operating on empirical knowledge, a recipe that produced a desired effect. Where a modern engineer calculates the load, the ancient artisan likely tasted the vinegar to check its strength and watched the bubbles to ensure the device was alive. The physical limitations of the Baghdad Battery also shed light on why it did not spark an earlier industrial revolution. Without copper wire to transmit the power over distances, the electricity was trapped within the immediate vicinity of the jar. The artifacts show no terminals or binding posts, suggesting that any connections were temporary, perhaps made by simply touching wires to the rim of the metals. This lack of infrastructure meant the energy could not be networked or distributed. It was a localized tool, likely sitting on a workbench alongside hammers and chisels, used for a specific craft rather than a universal power source. The transition from a curiosity or a specialized tool to a civilization-changing technology requires not just the invention of the cell, but the invention of the circuit, the switch, and the load. In the analysis of the electrolyte, researchers have also considered the possibility of other agents. Some theories propose the use of citric acid, though citrus fruits were not widely cultivated in the region at the time. Others suggest the use of mineral acids derived from naturally occurring sulfates, which would have drastically increased the power output, but would also have dissolved the iron rod much faster. The consensus leans toward fermented grape vinegar because it balances availability with functionality. The residue found inside the original jars was analysed and showed traces of organic compounds consistent with vinegar-like substances. This cements the idea that the battery was powered by the agricultural surplus of the civilization, literally running on the products of the vineyard. The reconstruction of the Baghdad Battery forces a recalibration of the timeline of scientific history. It demonstrates that the components for the electrical age were assembled and functional more than a millennium before Galvani noticed a twitching frog leg. The device is not a perpetual motion machine or a magical artifact. It is a clumsy, inefficient yet undeniably working galvanic cell. It produces direct current. It obeys Ohm's law. When a modern multimeter is hooked up to a replica fueled by grape vinegar, the numbers on the screen do not lie. The electrons flow from the iron to the copper, driven by the same electromotive force that powers a smartphone today. The difference is merely one of refinement and scale. This electrochemical reality suggests that the ancient world was not devoid of complex energy manipulation, but rather that their application of it was subtle. If the battery was used for electroplating, the evidence of its success would be hidden in plain sight, on the gilded surfaces of statues and jewellery that archaeologists have assumed were made using fire-gilding techniques involving mercury. The battery offers a safer, albeit slower alternative to mercury gilding, which was known to be toxic even in antiquity. The existence of such a device implies a level of chemical knowledge where the properties of metals and fluids were understood well enough to create a consistent, repeatable reaction. Ultimately, the study of the Baghdad Battery through the lens of modern electrochemistry reveals a functional, logical device. It strips away the mysticism and replaces it with the smell of vinegar and the corrosion of iron. It shows us that the magic of the ancients was often just chemistry that had not yet been named. The The jar, the cylinder, and the rod form a complete system, waiting only for the acid to wake it up. It stands as a silent witness to the fact that the principles of the universe are constant, waiting to be discovered, lost, and discovered again. The electrons moving through the iron rod in a dusty workshop in Mesopotamia obeyed the same laws as the electrons moving through the grid of a modern city. The only difference was the vessel that contained them. The most compelling argument for the existence of the Baghdad Battery lies not in the voltage it produces, but in the physical evidence left behind on the metalwork of the era. When archaeologists examine the intricate jewellery and ornaments of the Parthian and Sassanid periods, they frequently encounter items that defy simple explanation. These objects, often made of copper or bronze, possess a surface layer of gold so thin and uniform that traditional mechanical gilding techniques struggle to account for them. The standard method of the ancient world was foil gilding, where thin sheets of gold were hammered onto a base metal, or fire gilding, which involved a toxic mixture of mercury and gold paste heated until the mercury vaporized. However, microscopic analysis of certain artifacts reveals a deposition layer that lacks the telltale chemical signature of mercury and is far too consistent to be the result of hammering. This microscopic anomaly points directly to the electrochemical potential of the ceramic jars found in Kujut Rabu. Electroplating represents the most logical industrial application for a low-voltage, steady current device in an era without electric motors or light bulbs. The process, known today as electrodeposition, involves using an electric current to reduce dissolved metal cations so that they form a thin, coherent metal coating on an electrode. In the context of a Mesopotamian workshop, the setup would have been surprisingly simple, yet chemically sophisticated. The artisan would connect the iron rod of the battery to the object intended for plating, perhaps a copper statuette or a silver belt buckle, and submerge both in a solution containing dissolved gold salts. As the battery generated its steady flow of electrons, gold atoms would migrate from the solution and bond, atom by atom, to the surface of the base metal. This cold method of gilding would have seemed nothing short of miraculous to an observer, transforming a dull brown metal into a gleaming golden treasure without the intense heat or deadly fumes associated with mercury gilding. The technical requirements for such a feat are well within the capabilities of the Baghdad Battery, provided the artisans understood the necessity of patience and parallel processing. A single jar, producing roughly 1 volt, would deposit gold very slowly. To achieve a durable coat on a larger object, the ancient engineers likely wired multiple jars together. While no wires were found with the original artifacts, the corrosion patterns on the iron rods suggest they were once connected to external conductors. Strips of lead, iron, or copper could easily have served as the bridge between the power source and the plating tank. The result would be a galvanic array capable of sustaining the plating process for hours or days. This slow accumulation of gold creates a bond at the molecular level, far stronger than adhesive foil and far safer than mercury amalgam. It allowed for the mass production of gold items that were affordable to the merchant class, creating a booming market for imitation luxury goods. This economic context is crucial for understanding why such a device would be invented and utilized. In the ancient empires of the Near East, gold was the ultimate status symbol, yet it was scarce and exorbitantly expensive. Solid gold artifacts were the exclusive province of kings and high priests. However, the rising middle class of the Parthian Empire desired the aesthetic of power without the ruinous cost. Electroplating offered a technological solution to a socio-economic problem. It allowed craftsmen to stretch a small amount of gold over a vast surface area. A few coins worth of gold, dissolved in an electrolyte, could gild dozens of copper bracelets. This efficiency would have given any workshop possessing the secret jars a massive commercial advantage. They could produce goods that looked identical to solid gold but sold for a fraction of the price, effectively democratizing luxury through hidden chemistry. The evidence for this practice is often hidden in the corrosion itself. When a plated object survives for 2,000 years, the base metal underneath frequently corrodes, expanding and cracking the thin gold layer above. Archaeologists have found numerous items where the gold surface remains surprisingly intact while the copper core has disintegrated, leaving a hollow gold shell. This phenomenon supports the electroplating theory because it indicates a structural independence between the layer and the substrate that is characteristic of deposition. Furthermore, Modern reproductions of the battery, when used with gold electrolytes derived from ancient recipes, produce a layer indistinguishable from these historical samples. The science confirms the capability, the artifacts confirm the possibility. The only missing link is a written record, which is unsurprising given that trade secrets of this magnitude were rarely written down, but rather guarded jealously by guilds and families. However, the utility of the Baghdad Battery may have extended beyond the workshop and into the temple. While electroplating explains the industrial logic, it does not account for the mysterious nature of the object itself, a hidden source of power concealed within a common clay pot. This concealment has led some researchers to propose a more theatrical or religious application. In a world where electricity was unknown, a mild electric shock would have been interpreted as a supernatural force. If a series of these jars were connected to a metal idol or the gates of a sanctuary, they could deliver a surprising, tingling jolt to anyone who touched them. This presence of the god would have been a powerful tool for the priesthood, tangible proof that the deity inhabited the statue. The sensation produced by 1 or 2 volts is not painful, but it is undeniable, a buzzing vibration that feels like a living energy coursing through the metal. This theory of theurgical electricity aligns with what we know of other ancient mechanical marvels, such as the automatic doors of Hero of Alexandria, which were designed to inspire awe and reinforce the power of the temple. A priest knowing how to harness this invisible force could manipulate the experience of the worshipper. Imagine a scenario where a supplicant is told to touch the hand of a statue to see if their offering is accepted. If the priest completes the circuit, the statue bites or tingles, signaling a divine response. This application requires no understanding of electrons or ions, only a cause and effect knowledge. Connect the jars, and the metal comes alive. The lack of wires found at the dig site might simply mean that the conductors were removable, set up only for specific rituals and then hidden away to preserve the mystery. There is also a medical dimension to the application of this early electricity. Ancient texts from Rome and Greece mention the use of electric torpedo fish to treat pain, particularly gout and headaches. The shock from the fish was known to numb the nerves and provide temporary relief. It's entirely plausible that the Baghdad Battery was developed as a synthetic alternative to the electric fish. A portable, controllable source of numbing vibration would have been a valuable medical device in a world with few effective painkillers. By applying the iron rod to an aching joint or a throbbing temple, a healer could administer a localized shock to disrupt pain signals. While this theory is harder to prove archaeologically than the electroplating, it fits the human tendency to use every available tool to alleviate suffering. The voltage generated is consistent with modern TNs, transcutaneous electrical nerve stimulation units, suggesting that the ancients may have stumbled upon electroanalgesia millennia before it was formally understood. Regardless of whether it was used for greed, God, or healing, the practical application of the Baghdad Battery relied on a deep, empirical understanding of materials. The artisans who maintained these devices had to know how to refresh the electrolyte, likely using vinegar or fermented grape juice, and when to replace the corroded iron rods. They were managing a chemical reaction without a periodic table, relying on the smell of the acid, the colour of the bubbles, and the taste of the current. Quite literally, as early electricians often tested voltage by placing wires on their tongues, this sensory relationship with electricity is a far cry from our detached, insulated modern experience. To the user of the Baghdad Battery, electricity was a fluid, a living thing that had to be fed and maintained, a force that could plate a necklace or shock a non-believer depending on how it was directed. The existence of such specific applications challenges the view of ancient technology as merely ornamental or accidental. Electroplating is a precision industry. It requires controlling variables like solution strength, temperature, and time. If the Parthians were indeed plating jewellery, they were engaging in process engineering. They were standardizing a chemical output to achieve a consistent commercial product. This implies a level of sophistication in their manufacturing sector that history books often overlook. It suggests that the dark ages of technology were not dark because of a lack of capability, but because the knowledge was compartmentalized, protected, and eventually lost when the economic or social structures supporting it collapsed. Ultimately, the physical reality of the gilded artifacts serves as the most enduring testament to the battery's purpose. We find copper objects that should have turned green and crumbled to dust, yet they shine with the luster of gold. We find layers of precious metal so fine they measure in microns, defying the hammer and the fire, These objects are the silent witnesses to a forgotten industrial revolution that occurred in the clay jars of Mesopotamia. They prove that the electrons flowing through the iron rod were not just a scientific curiosity. They were put to work. They added value to goods. They perhaps added mystery to religion. And they certainly added a layer of complexity to our understanding of the past. The battery was a tool, and like any tool, its significance is defined by what the human hand chose to build with it. The storm that drove Captain Dimitrios Kontos to seek shelter off the rocky islet of Antikythera in the spring of 1900 was a fortunate accident of history that would ultimately rewrite the timeline of human technology. His crew of sponge divers from the island of Symi were not seeking archaeological treasures. They were waiting for the gale to subside so they could harvest natural sponges from the deep Mediterranean floor. When the weather cleared, they decided to dive the unfamiliar waters, perhaps hoping to make up for lost time. Elias Stadiates, one of the divers, donned his heavy canvas suit and copper helmet. Descending 45 meters into the gloom, he signaled frantically to be pulled up almost immediately. When his helmet was removed, he was rambling about a heap of rotting corpses, men, women, and horses scattered on the seabed. He had not found bodies, but a graveyard of bronze and marble statues, the cargo of a massive Roman shipwreck that had lain undisturbed for 2,000 years. What followed was the first major underwater archaeological excavation in history, though it was conducted with the crude and dangerous methods of the turn of the 20th century. The divers hauled up magnificent bronzes, including the famous Ephebi of Antikythera and the Philosopher's Head, working at depths that induced nitrogen narcosis in the bends. The cost of recovery was high, with one diver dying and others suffering permanent paralysis, but the haul was spectacular. Amidst these artistic treasures, a calcified, shapeless lump of bronze and wood was recovered, almost as an afterthought. It was tossed into a crate overshadowed by the statues and shipped to the National Archaeological Museum in Athens. For 2 years it sat in a courtyard, drying out and breaking apart, dismissed as a piece of scrap metal or perhaps a part of the ship's capstan. It was ugly, corroded, and seemingly insignificant compared to the masterpieces of Hellenistic art surrounding it. The true discovery happened not on the seabed, but in the dry air of the museum. In May 1902, archaeologist Spiridon Stace was examining the fragments when he noticed that the drying wood had split open the calcified mass. Embedded within the corrosion was something that should not have been there: a precision-cut bronze gear wheel with distinct, triangular teeth. The presence of a gear in a shipwreck dated to the 1st century BC was an archaeological impossibility. At that time, the prevailing historical consensus was that geared mechanisms of such refinement did not appear until the rise of mechanical clocks in medieval Europe, more than a millennium later. The cognitive dissonance was so strong that many scholars initially dismissed the artifact as a modern contamination, suggesting a clock from a passing ship had accidentally fallen onto the ancient wreck site and fused with the older debris. For decades the device remained a contentious puzzle, its inner workings obscured by layers of hard corrosion and sea accretion. It was not until the mid-20th century that technology caught up with the artifact. In the 1950s, a British physicist and historian of science named Derek de Solla Price began a systematic study of the fragments. He realized that standard visual inspection was useless. The secrets of the mechanism were locked inside the stone-like lumps. In 1971, Price teamed up with the Greek radiographer Charalampos Karakalos to subject the fragments to gamma-ray imaging. The resulting ghostly images were a revelation. They revealed not just one gear, but a complex train of at least 30 interlocking gears crowded together in layers of intricate engineering. This was no navigational astrolabe or simple toy. It was a machine of staggering complexity. Price's analysis shifted the conversation from identification to disbelief. The X-rays showed a differential gear arrangement, a level of mechanical sophistication that was previously thought to have been invented in the 16th century. Price published his findings in a landmark 1974 paper, declaring it a calendar computer. However, the two-dimensional nature of the X-rays left many questions unanswered. The gears were overlapping in the images, making it difficult to trace the transmission of motion from one wheel to the next. The reconstruction was still largely hypothetical, a shadow play of mechanics that hinted at genius but refused to fully reveal it. Without a three-dimensional view, researchers could not be certain how the gears engaged or what specific cycles they were calculating. The definitive breakthrough arrived in 2005 with the formation of the Antikythera Mechanism research project. A coalition of international scientists brought distinct cutting-edge technologies to Athens specifically for this artifact. Hewlett-Packard developed a specialized imaging system called polynomial texture mapping to enhance the surface details, while X-Tech Systems from the UK brought a 12-ton microfocus X-ray computed tomography machine. This was not a medical CT scan. It was an industrial-grade device designed to look for microscopic cracks in turbine blades. Because the machine was too heavy to move into the museum and the artifact too fragile to travel, the team had to navigate a bureaucratic and logistical nightmare to bring the mountain to the profit, installing the massive scanner inside the museum itself. The resulting data was breathtaking. The CT scans sliced through the artifact digitally, allowing researchers to peel away the corrosion layers virtually. They could now see the mechanism in 3 dimensions, isolating individual gears, measuring the precise count of teeth, and inspecting the geometry of the teeth themselves. This precision was critical because the number of teeth on a gear determines its mathematical function. A gear with 53 teeth or 127 teeth implies specific astronomical cycles. The scans revealed that the device was not merely a clock, but a dynamic model of the cosmos. It tracked the movements of the sun and moon, predicted eclipses, and even modeled the irregular orbit of the moon, an anomaly caused by its elliptical path around the Earth, using a pin and slot mechanism that varied the speed of the gear rotation. Perhaps the most stunning revelation from the modern imaging was the discovery of text. The corrosion that had encased the mechanism had also preserved the faint traces of Greek inscriptions etched onto the bronze plates and covers. The CT scans and surface imaging allowed philologists to read thousands of characters that had been invisible to the naked eye for 2,000 years. This was the user manual of the device. It confirmed the names of the months, the cycles being tracked, and even described parts of the mechanism that were missing or lost to the sea. The text provided the context that the gears alone could not, proving that this was a public instrument, likely used for teaching or demonstration, rather than a hidden occult tool. It described the colour of future eclipses and the specific winds associated with them, blending astronomy with the astrological needs of the time. Reconstructing the device from these digital ghosts was a task of immense difficulty. The mechanism is fragmented into 82 known pieces, with 7 large fragments containing the bulk of the mechanism and dozens of smaller bits that are little more than bronze dust. Researchers had to mentally and digitally reassemble a machine that had been crushed by the pressure of the sea and the weight of the shipwreck. They had to account for the deformation of the metal plates and the migration of components over 2 millennia. It was like solving a 3-dimensional puzzle, where half the pieces are missing, the box is lost, and the picture on the front changes depending on who you ask. Yet, the mathematical logic of the gear trains provided a guide. If one gear drives another to represent the metonic cycle of the moon, the ratio of teeth must be exact. The math served as the blueprint where the metal had failed. The reconstruction efforts highlighted a severe disconnect between our perception of ancient capabilities and the reality of their engineering. Early attempts to build physical replicas often failed because modern machinists struggled to replicate the hand-cut triangular teeth of the original. The ancient mechanic did not have a lathe or a gear-cutting machine. They filed these gears by hand with a precision that rivals modern manufacturing. The spacing of the teeth was uniform, the angles precise, and the axles perfectly aligned. This realization forced a re-evaluation of the entire history of technology. It became clear that the Antikythera mechanism was not a prototype, but a mature device. It showed signs of wear and repair, and its design was confident and refined, suggesting it was the product of a long tradition of mechanical engineering that has otherwise vanished from the archaeological record. The timeline of scientific understanding of the device reflects the slow erosion of modern arrogance. In the early 1900s, it was a mistake. In the 1950s, it was a curiosity. By the 1970s, it was an anomaly. Today, it is recognized as the pinnacle of ancient Greek technology. The journey from a lump of corroded bronze to the first computer required the invention of technologies that the Greeks themselves could never have imagined. We needed X-ray tomography to see what they built with files and bronze sheets. The discovery proves that technological progress is not a steady ascent, but a jagged landscape where high peaks of knowledge can be followed by deep valleys of forgetting. the mechanism sat on the ocean floor for 2,000 years, holding the secrets of the cosmos in its gears, waiting for a civilization advanced enough to read them. The internal architecture of the Antikythera Mechanism represents a level of mechanical sophistication that vanishes from the historical record for nearly 1,800 years after its construction. At the heart of this bronze computer lay a complex arrangement of at least 30 meshing gears, compacted into a wooden frame no larger than a shoebox. The primary input was a hand crank located on the side of the box, which turned a large central gear representing the sun. This was not merely a clock that ticked forward at a constant rate, but a variable calculator. By rotating the crank, the operator could move forwards or backwards in time, setting the date and watching the heavens rearrange themselves to match. The central, sun gear drove the entire system, distributing motion through a branching network of gear trains that performed simultaneous calculations for the cycles of the moon, the position of the sun, and the timing of eclipses. The mathematical foundation of these gear trains relied on the precise ratios of teeth, derived from centuries of Babylonian and Greek astronomical observations. The designers faced a fundamental problem of the cosmos. The cycles of celestial bodies do not fit neatly into one another. A lunar month is not a whole number of days, and a solar year is not a whole number of lunar months. To solve this, the mechanism utilized the Metonic cycle, a period of 19 years, which almost exactly equals 235 lunar months. The engineers translated this arithmetic relationship into metal. By creating a gear train with specific tooth counts, such as a 38-tooth gear driving a 48-tooth gear, which in turn drove a 127-tooth gear, they could mechanically divide the motion to represent these distinct time frames. The result was a main dial on the front of the mechanism that displayed the date in the Egyptian calendar and the position of the sun and moon in the zodiac, while simultaneously driving spiral dials on the back. One of the most startling engineering features was the mechanism's ability to model the variable velocity of the moon. Ancient astronomers knew that the moon does not move across the sky at a constant speed. It accelerates when it is closer to the Earth and slows down when it's further away, a phenomenon caused by its elliptical orbit. To replicate this without the modern understanding of gravity or ellipses, the Greek engineers invented a pin and slot mechanism. Two gears were stacked directly on top of one another, sharing the same axis but not the same center of rotation. One gear had a pin that slotted into the other gear. As the bottom gear turned, the pin drove the top gear, but because the centers were slightly offset, the leverage changed throughout the rotation. This caused the top gear to speed up and slow down in a rhythmic cycle that perfectly mimicked the moon's anomaly. This specific assembly is a mechanical masterpiece that physically models a complex harmonic function, a solution that would not reappear in machinery until the clocks of the Renaissance. The rear of the mechanism was dominated by two large spiral dials, a design choice necessitated by the need for high resolution. A simple circular dial would have been too small to display the necessary divisions of time, so the engineers coiled the scales like a record groove. The upper back dial displayed the Metonic cycle of 235 months. A pointer with a small follower tip tracked along the spiral groove, extending and retracting as it moved from the center to the edge. This 5-turn spiral allowed the user to correlate the lunar calendar with the solar calendar, essential for agricultural planning and religious festivals. Inside this dial was a smaller subsidiary dial for the Callippic cycle, a 76-year period that further refined the accuracy of the Metonic cycle, demonstrating that the device was built for long-term stability and precision. Below the Metonic spiral lay the Saros dial, which was engineered to predict eclipses. The Saros cycle is a period of approximately 18 years, 11 days and 8 hours, after which identical solar and lunar eclipses repeat. The mechanism calculated this cycle to warn the user of upcoming celestial events. The dial was divided into 223 sections, representing the lunar months in the cycle. Specific months possessed glyphs indicating whether a solar or lunar eclipse would occur and at what hour. Because the Saros cycle includes a fractional 8 hours, the eclipse would occur at a different time of day and potentially be visible from a different part of the world. To account for this, a smaller subsidiary dial, the Exeligmos, tracked a triple Saros cycle of 54 years, allowing the user to add 8, 16 or 24 hours to the prediction, thereby standardizing the time calculation. Beyond the astronomy, the mechanism also functioned as a social and athletic calendar. A small dial near the Metonic spiral displayed the 4-year cycle of the Panhellenic Games, including the Olympics, the Pythian, the Nemean, and the Isthmian Games. This inclusion grounds the device in the cultural reality of ancient Greece. It suggests that the mechanism was not purely an instrument of abstract science, but a tool for organising society. The synchronization of the heavenly bodies was intrinsically linked to the synchronization of human events. Knowing when to hold the games was as vital as knowing when the moon would darken. This dial used a simple internal gearing system to rotate a pointer through 4 quadrants, each inscribed with the names of the locations where the games were held, serving as a regulating heartbeat for the Greek world. The manufacturing techniques required to build such a device challenge our understanding of ancient metallurgy and craftsmanship. The gears were not cut by hobbing machines or stamped out by presses. They were handcrafted from bronze sheet metal. Analysis of the teeth shows that they were equilateral triangles, filed with an angle of 60 degrees. The precision required to file 223 teeth on a gear only a few inches in diameter, ensuring the spacing was uniform enough to prevent jamming, is immense. The metal itself was a low-tin bronze alloy, likely cold-worked to increase its hardness. The specialised artisans who built this did not merely follow a theoretical blueprint. They possessed a tactile understanding of tolerance and friction. They used washers and spacers to keep the gears aligned and secured them with pins and wedges. The existence of correction holes in some gears suggests that if a mistake was made during the division of the circle, the mechanic would rotate the plate and start again, prioritising mathematical exactness over material cost. This device fundamentally alters the definition of the word computer in a historical context. It is strictly an analog computer, a physical system that uses continuous variables, in this case, the rotation of gears, to model mathematical relationships. It accepts an input, processes it through a predetermined algorithm encoded in the gear ratios, and delivers an output on the dials. It does not store a program in the modern sense, but the program is built into the hardware. The gear ratios are the software. By physically connecting the motion of the sun to the motion of the moon, and the timing of eclipses, the Antikythera Mechanism proves that the ancient Greeks viewed the universe as a machine. If the cosmos was a set of predictable, interlocking cycles, then it could be simulated by a set of predictable, interlocking gears. The level of miniaturization found in the mechanism suggests a mature technology, not an experimental prototype. The components are tightly packed, with layers of gears sandwiched millimeters apart. This density implies that the makers had already solved the problems of friction and axle strength in previous, larger iterations. There is no wasted space inside the casing. The front and back plates were covered in inscriptions, essentially a user manual in a star almanac, engraved with letters less than 2 millimeters high. These texts detailed the rising and setting of various stars and constellations, correlating them with the dates on the dials. This integration of text and mechanics indicates that the device was intended to be a comprehensive reference tool, a portable encyclopedia of astronomy that could answer specific questions about the state of the heavens at any given moment in the past or future. The survival of the Antikythera mechanism is a statistical miracle that forces us to confront the gaps in the archaeological record. Bronze was a valuable commodity, and broken or obsolete machines were almost always melted down to make coins, weapons, or statues. This device only survived because it was removed from circulation by a shipwreck, preserved by the very catastrophe that destroyed it. Its complexity implies the existence of a workshop tradition, a lineage of masters and apprentices who passed down the knowledge of gear ratios and epicyclic motion. It is highly improbable that this was a unique, singular creation. Just as a modern laptop implies the existence of a global electronics industry, the Antikythera mechanism implies an ancient industry of high-precision mechanics, of which we have found only this single, corroded sample. Understanding the engineering of the Antikythera mechanism requires stripping away the assumption that technological progress is linear. The specific combination of differential gearing, pin and slot mechanisms, and spiral dials represents a peak of engineering that was not surpassed until the astronomical clocks of the late Middle Ages. The intellectual leap required to translate the elliptical orbit of the Moon into a mechanical variation of speed is profound. It shows that the ancients were not limited by their intelligence or their grasp of mathematics, but only by their materials and power sources. They had the mind of the clockmaker long before they had the steel springs and escapements of the modern era. The mechanism stands as a testament to a lost age of logic, where bronze gears turned in silence to mimic the dance of the stars. The sheer existence of the Antikythera Mechanism fundamentally rewrites the history of technology and dismantles the traditional timeline of human innovation. Before its discovery, the prevailing historical narrative suggested that complex geared mechanisms were a product of the late Middle Ages, evolving slowly toward the clockwork of the Renaissance. This artifact proves that the timeline is not a steady upward slope, but a jagged landscape of peaks and valleys. The Greeks possessed a level of mechanical sophistication in the 2nd century BC that would not be seen again in Europe for nearly a millennium and a half. This realization forces a complete reassessment of ancient capabilities, suggesting that what we perceive as the scientific revolution of the modern era may actually be a rediscovery of principles that were mastered and then tragically lost. This device serves as physical evidence that the ancient Greeks were not merely philosophers and theoreticians, but also master engineers capable of translating abstract mathematical concepts into tangible, functioning hardware. The intricate gearing required to model the Saros cycle, or the variable velocity of the Moon, implies a deep synergy between the astronomer and the mechanic. It suggests that the workshops of Rhodes or Syracuse were not just producing static statues or simple pulleys, but were centres of high-precision manufacturing. The craftsmen who built this machine had access to tools and techniques for cutting triangular gear teeth with consistent pitch and angle, a feat that requires more than just a steady hand. It requires a systematic understanding of metallurgy and geometry that borders on industrial standardization. The cultural connection between this mechanism and the astronomical knowledge of the period is profound. The device is not a calculator in the modern sense of creating new data, but rather a simulator of the cosmos as understood by the Hellenistic world. It embodies the geocentric model of the universe, physically demonstrating the belief that the heavens operated according to fixed, mathematically knowable laws. By encapsulating the cycles of the Babylonians, who provided the raw data on eclipse intervals, and the geometry of the Greeks, who provided the spatial reasoning, the mechanism represents a synthesis of centuries of Mediterranean and Mesopotamian science. It functioned as a portable planetarium, likely used for teaching or demonstration, allowing a user to hold the cosmos in their hands and fast forward through time to predict the will of the gods or the turning of the seasons. Historical records from the period corroborate the existence of such devices, though for centuries scholars dismissed these accounts as exaggeration or metaphor. The Roman orator Cicero, writing in the 1st century BC, described a sphere constructed by his friend Posidonius that reproduced the movements of the Sun, Moon, and 5 planets. He also mentioned a similar device created by Archimedes that was taken to Rome after the siege of Syracuse. For a long time, historians treated these descriptions as literary flourishes. The Antikythera Mechanism vindicates Cicero, transforming his writings from mythological praise into accurate technical reporting. It confirms that the device found in the shipwreck was not a singular, magical anomaly, but a surviving example of a wider tradition of mechanical celestial globes that were circulating among the intellectual elite of the Roman Republic. The question of influence on subsequent mechanical calculators is complex, defined more by the tragedy of the break in the lineage than by continuity. While the Antikythera Mechanism displays the earliest known use of a differential gear, a system that allows 2 shafts to rotate at different speeds, essential for calculating the phase of the Moon, this specific technological leap appears to have vanished from the historical record. The differential gear would not be reinvented until the industrial era to solve problems in textile manufacturing and later in automobiles. This suggests that while the general concept of geared mechanisms survived in simpler forms, such as the Byzantine sundial calendars and later Islamic astrolabes, the high-end mastery of epicyclic gearing died out with the decline of the Greco-Roman world. The knowledge did not flow smoothly into the future, it evaporated, leaving humanity to slowly reinvent the wheel, or in this case, the gear train. This loss represents a catastrophic regression in technological capacity. The collapse of the Roman Empire and the subsequent economic fragmentation meant that the social structures required to support such specialized craftsmanship disintegrated. Complex machines require a stable economy, a class of wealthy patrons, and a system of apprenticeship to pass down proprietary secrets. When these support systems failed, the machines were not just stopped, they were melted down. Bronze was too valuable to be left in the form of a broken calculator when it could be recast into a sword or a coin. The Antikythera Mechanism only survived because it was lost at the bottom of the sea, safe from the recycling furnaces that likely claimed its sister devices. This highlights the fragility of advanced technology. Without continuous transmission and preservation, even the most brilliant inventions can be erased from memory within a few generations. The educational value of the mechanism in the modern era lies in its ability to humble our perspective on the past. Replicas built by researchers like Michael Wright and teams at various universities have demonstrated the immense difficulty of constructing such a device even with modern knowledge. Wright, who built a working model using only tools that would have been available in antiquity, showed that the ancient makers were not just clever, they were disciplined experts. The replicas reveal that the mechanism was designed with user-friendliness in mind, featuring a user manual inscribed on the casing and colour-coded dials for easy reading. This was a finished consumer product, not a rough prototype, which implies a maturity of design thinking that rivals modern industrial engineering. Studying the mechanism also bridges the gap between the humanities and the hard sciences. It shows that the study of history is not just about texts and wars, but about the history of rational thought and engineering. The device is a testament to the human desire to predict and control the environment. In a world without electric light or digital clocks, knowing the exact phase of the moon or the timing of the next eclipse was a way to impose order on a chaotic existence. The mechanism offered a sense of certainty. By turning the handle, a priest or a politician could see the future layout of the sky, linking the mechanical movements of the gears to the divine movements of the stars. It blurred the line between science and religion, serving as a tool for both navigation and divination. The rediscovery of this artifact has also spurred a new field of experimental archaeology, where researchers use X-ray tomography and computer modelling to peer inside corroded lumps of metal. This non-invasive dissection has revealed that the mechanism contained at least 30 gears, and potentially more that have been lost. The density of the components is startling, resembling the interior of a 19th century Swiss watch rather than an ancient relic. This density proves that the Greeks had solved problems of friction, torque, and axial strength that we assumed were stumbling blocks for ancient engineers. They understood that by miniaturizing the mechanism, they could reduce the weight and the wear on the moving parts, a principle of efficiency that remains valid today. Ultimately, the Antikythera mechanism stands as a monument to what could have been. It provokes a haunting question about the trajectory of human progress. If the knowledge embodied in this device had been preserved and built upon, rather than lost for 18 centuries, the mechanical revolution might have occurred 1,000 years earlier. We might have seen steam engines or complex automation in the medieval period. Instead, the mechanism remained a silent secret on the ocean floor, a time capsule of genius that the world was not ready to maintain. Its recovery serves as a stark reminder that progress is not guaranteed. Knowledge is not a permanent inheritance. It is a fragile flame that must be actively protected, lest it be extinguished by the shifting tides of history and economics. The mechanism is not just a computer, it is a warning. In the 1st century AD, the intellectual centre of gravity for the Mediterranean world was not Rome, despite its military might, but Alexandria in Egypt. This city was a fusion of Greek theory and Egyptian pragmatism, a sprawling metropolis dominated by the Great Library and the Pharos Lighthouse. It was here, amid the smell of papyrus and the noise of the harbour, that a mathematician and engineer known as Hero, or Heron, lived and worked. While the Antikythera mechanism demonstrated the Greek mastery of cyclical time and astronomy, Hero's work represented something perhaps even more modern: the mastery of physics to manipulate the physical environment. He was not merely a philosopher pondering the nature of the soul, he was an inventor obsessed with air pressure, water, steam, and the mechanical advantage of levers and gears. Hero is best understood through his surviving texts, particularly the Pneumatica and the Automata, which read less like ancient scrolls and more like engineering manuals or patent applications. These documents reveal a mind that viewed the natural world as a system of forces that could be harnessed for human utility, or more often for human entertainment. In the context of Hellenistic Alexandria, science was frequently employed for thaumaturgy, the creating of wonder. The goal was often to dazzle the public or the devout, creating illusions of divine intervention that were, in reality, rigorous applications of hydraulic and pneumatic principles. Hero was the master of this theatrical engineering, creating devices that blurred the line between magic and machine. One of the most spectacular examples of this synthesis was Hero's design for automatic temple doors. To the average worshipper approaching a temple, the experience was supernatural. A priest would light a fire on an altar outside the temple, and as the flames rose, the massive doors to the inner sanctum would slowly swing open on their own, revealing the god statue within. When the fire was extinguished, the doors would close. There were no ropes pulled by hidden servants, only the visible action of the fire. The mechanism behind this miracle was a brilliant application of the expansion of gases. Beneath the altar lay a sealed air chamber connected by a tube to a vessel of water underground. As the altar fire heated the air in the chamber, the air expanded, forcing its way down the tube and pushing the water out of the vessel into a second bucket suspended by a rope. This transfer of water caused the bucket to become heavier. The bucket was attached to a system of ropes and pulleys wound around the vertical axles of the doors. As the bucket descended under the weight of the displaced water, it pulled the ropes, rotating the axles and opening the doors. When the fire died down, the air in the altar chamber cooled and contracted, creating a partial vacuum. The water was siphoned back from the bucket into the original vessel, lightening the load. A counterweight then pulled the doors shut. This was a fully automated thermal engine, utilizing heat energy to perform mechanical work, designed not for industry, but to instill religious awe. It demonstrates that the principles of thermodynamics were being utilized in practical, albeit theatrical applications nearly 2 millennia before the invention of the modern steam engine. Even more surprising to the modern observer is Hero's invention of the world's first vending machine. Today we associate automated dispensaries with electricity and microchips, but Hero achieved the same result with simple mechanics. Outside temples, holy water was a necessary but often wasted resource. To regulate its distribution, Hero designed a device comprising a sealed vessel with a slot at the top. When a believer dropped a 5 drachma coin into the slot, the coin fell onto a specialized pan attached to a lever. The weight of the coin depressed the lever, which raised a valve at the bottom of the tank, allowing a measured amount of holy water to flow out of a spout. As the pan tilted further, the coin slid off, causing the lever to snap back into place and the valve to close, cutting off the flow. This device relied entirely on the specific weight of the currency and the precise calibration of the lever, creating a transaction that was fair, automated, and required no human attendant. The sophistication of these devices highlights a critical realization about ancient engineering. They understood the if-then logic that underpins modern programming. Hero's designs were essentially mechanical programs. If fire is lit, then open doors. If coin is deposited, then release water. This logic extended to his theatres of automata, programmable puppet shows powered by falling weights and slowly releasing grain or sand. These miniature theatres could perform entire plays, with figures moving, doors opening, and sound effects playing, all driven by a pre-calculated sequence of mechanical interactions. The text of the automata describes the use of knotted ropes acting as the software to trigger specific actions at specific times, a concept that predates the punch cards of the Jacquard loom or early computing by 18 centuries. However, the most tantalizing of Hero's inventions is the Aeolipile, a device that brings the narrative of ancient technology to a frustrating climax. The Aeolipile consisted of a water-filled cauldron heated by a fire. A lid covered the cauldron, with 2 bent pipes rising from it to hold a hollow sphere. Steam generated in the cauldron rose through the pipes and entered the sphere. The sphere had 2 L-shaped nozzles pointing in opposite directions. As the steam blasted out of these nozzles, the force of the escaping gas generated torque, causing the sphere to spin rapidly. This was, by definition, a reaction turbine. It converted thermal energy into rotary motion using the same principle of jet propulsion that powers modern aircraft and rockets. The existence of the Aeolipile forces historians and engineers to confront a difficult question. Why did the Industrial Revolution not begin in Alexandria in the 1st century? The components were there. They had the gear trains found in the Antikythera Mechanism, the piston pumps used in fire engines, and the steam power of the Aeolipile. Theoretically, these could have been combined to create machines capable of grinding grain, sawing wood, or pumping water on an industrial scale. Yet, the Aeolipile remained a curiosity, a philosophical toy, used to demonstrate principles of physics rather than to drive the economy. It spun on tabletops, entertaining guests, while the heavy lifting of the empire continued to be done by human and animal muscle. The answer to this stagnation lies not in a lack of intelligence, but in the structure of ancient society. The Roman world was built on the foundation of slavery. When human labour is abundant and cheap, essentially free, aside from the cost of food, there is no economic pressure to invent labour-saving devices. Innovation is often driven by scarcity. When labour is expensive, capital invests in machinery. In Hero's world, the elite had no incentive to replace their slaves with steam engines. Furthermore, the cultural concept of techne or craftsmanship was viewed differently. Gentlemen philosophers engaged in abstract thought. Manual labour and the application of mechanics were often seen as beneath them, suitable only for amusement or religious ritual. The disconnect was not technical, but social and economic. Hero of Alexandria represents the apex of ancient applied mechanics, a moment when the pieces of the technological puzzle were laid out on the table. His writings preserved the knowledge of Ctesibius and Philo, passing down the secrets of pneumatics and hydraulics to the Islamic Golden Age, where scholars like Al-Jazari would later refine them. But in his own time, Hero's genius was encapsulated in the temple miracle and the parlour trick. The steam turbines spun, the temple doors opened, and the holy water flowed, but the feedback loop that drives rapid industrialization never materialized. The gears were turning, but they were not yet connected to the wheels of industry. The tragedy of Hero's world is not that they lacked the technology, but that they lacked the vision to apply it to the transformation of labour. The Aeolipile is a ghost of a future that never arrived, a testament to the fact that invention alone is insufficient for revolution. It requires a society ready to embrace the machine, a condition that would not arise for another millennium and a half. As we look back at the bronze sphere spinning in the Alexandrian heat, we see the fragility of progress, how close humanity came to a different history, and how easily the momentum was lost to the inertia of the status quo. The scene that greeted a worshipper in 1st century Alexandria was calculated to overwhelm the senses and suspend disbelief. A devotee would approach the temple of a god, standing before massive, imposing bronze doors that barred entry to the inner sanctum. There were no gatekeepers, no guards, and no visible mechanisms to operate the heavy barriers. The high priest would step forward, not to the doors, but to a small altar positioned prominently in front of the temple entrance. He would light a fire upon the altar, offering a burnt sacrifice to the deity. As the flames grew higher and the heat intensified, a low groan of machinery might be heard, masked by the chanting of the crowd. Then, slowly and smoothly, the massive doors would swing open on their own accord, revealing the statue of the god inside. To the average citizen, this was an undeniable manifestation of divine will, a miracle triggered by the offering of fire. To Hero of Alexandria, it was a triumph of pneumatic engineering and thermal dynamics. The secret to this divine intervention lay buried beneath the temple floor, hidden in a basement chamber, accessible only to the technical staff of the priesthood. The mechanism relied on a sophisticated understanding of the relationship between heat, air pressure, and fluid dynamics. The altar itself was not a solid block of stone, but a hollow, airtight vessel. When the fire was lit on the surface, the air trapped inside the hollow column began to heat up. Following the principles of thermodynamics, principles that would not be formally codified for another 1800 years, the heated air expanded. With nowhere to go inside the sealed altar, the pressurized air was forced down through a copper tube that ran through the floor and into a large spherical vessel filled with water. This transfer of energy initiated a chain reaction that converted thermal energy into mechanical force. The incoming pressurized air pushed against the surface of the water inside the sphere. Since the sphere was also airtight, the water had only one escape route, a siphon, which is essentially an inverted U-shaped tube leading out of the sphere and into a suspended bucket. As the pressure built, water was forced up the siphon and poured into the bucket. This was a precise application of fluid displacement. As the bucket filled with water, it became heavier. The increasing weight eventually overcame the resistance of a counterweight system, connected to it by a series of ropes and pulleys. The genius of Hero's design was in how he translated this vertical gravitational force into rotational motion. The ropes attached to the heavy water bucket were wound around two vertical spindles, which served as the pivot points for the temple doors above. As the bucket descended, it pulled the ropes, rotating the spindles and causing the doors to swing open. The timing was impeccable. The doors would open just as the fire reached its peak intensity, creating a seamless theatrical link between the sacrifice and the revelation of the god. The system even accounted for the end of the ceremony. When the fire on the altar burned out, the air inside the hollow chamber cooled and contracted. This created a partial vacuum which sucked the water from the bucket back through the siphon and into the original sphere. As the bucket became lighter, the counterweight descended, pulling the ropes in the opposite direction and gently closing the temple doors. This mechanism represents one of the earliest known examples of a feedback loop in engineering, where a change in the environment, the temperature of the altar, triggered a mechanical response that altered the state of the system. It demonstrates that the ancients understood that air was not simply empty space, but a physical substance that could be manipulated to perform work. Hero utilized the expansive property of gases to create a prime mover, effectively building a heat engine that operated without pistons or steam, yet achieved the same result of converting thermal energy into kinetic energy. While the automatic doors provided the spectacle, Hero also designed systems to handle the more mundane logistics of temple management, applying the same rigor to commerce as he did to miracles. Outside many of these temples stood another device that would seem utterly anachronistic to a modern observer: a coin-operated vending machine. In the ancient world, holy water was a necessary component of ritual purification, but distributing it required manpower and oversight to ensure that offerings were made. Hero automated this exchange with a device that dispensed a precise amount of water in exchange for a 5 drachma coin. The internal architecture of this vending machine was elegant in its simplicity, relying on the principles of levers and equilibrium. The machine consisted of a sealed vessel with a slot at the top and a spout at the bottom. Inside, a horizontal lever was balanced on a fulcrum. One end of the lever held a small pan positioned directly beneath the coin slot. The other end was connected to a vertical plug that sealed the water pipe. When a visitor dropped a coin into the slot, it fell onto the pan. The weight of the coin tipped the lever, lifting the plug at the other end and opening the valve. Water flowed out of the spout for the worshipper to collect. However, the machine did not simply empty itself. As the lever tilted, the pan angled downward until the coin slid off and fell into a collection box below. Once the weight of the coin was removed, a counterweight snapped the lever back to its original position, closing the valve and stopping the flow of water. This device effectively removed the human element from the transaction, creating a standardized, self-regulating system that functioned 24 hours a day without fatigue or error. It is a stark example of how early engineers conceptualized automation. They did not need microchips or sensors to create smart systems. They used gravity, balance, and mechanical geometry to create logical gates. The machine essentially performed a physical if-then calculation. If a coin of sufficient weight is introduced, then open the valve until the coin is processed. The integration of these technologies into religious spaces speaks to a complex relationship between science and society in the Greco-Roman world. These machines were not presented as technological marvels to be understood by the public. They were presented as magic. The priesthood utilized the disparity in knowledge between the engineer and the layperson to reinforce social hierarchies. The miracle of the opening doors served to validate the power of the priest and the presence of the god, using hidden pneumatics to manufacture ore. It was a form of psychological engineering, where the interface, the altar and the doors, was designed to hide the mechanism, creating a user experience that felt supernatural rather than mechanical. Hero's designs reveal that the fundamental components of automation were already present in the 1st century. The temple doors and the vending machine relied on inputs, processing, and outputs. The input was heat or a coin. The processing was the expansion of air or the tilting of a lever. The output was the motion of the doors or the flow of water. These were robots in the strictest sense of the word, machines capable of carrying out a complex series of actions automatically. The survival of these descriptions in Hero's text, Pneumatica, provides a blueprint of a lost potential, showing that the ancient world possessed the mechanical sophistication to automate labour and services, yet chose to apply this genius primarily to the theatre of the gods. The machinery of the future was already humming beneath the floorboards of the past, waiting for a world that was ready to use it for more than just a magic trick. The brilliance of Hero's design lies not merely in the dispensing of water, but in the precise calibration of the reset mechanism, which represents one of the earliest known applications of a self-regulating feedback loop in consumer engineering. A simple valve is relatively easy to construct, but a valve that closes itself requires a sophisticated understanding of equilibrium, restoring force, and the center of gravity. The internal lever of the device effectively functioned as a mechanical timer, a physical computer that calculated duration based on mass and friction. The length of time the water flowed was not arbitrary. It was dictated by the coefficient of friction between the bronze coin and the surface of the receiving pan. A heavier coin might generate more momentum, tilting the lever sharply and opening the valve fully, while a rougher coin might cling to the pan for a fraction of a second longer, extending the duration of the pour. This means that the customer's experience, the exact volume of holy water received, was a direct physical variable derived from the currency they used. It was an analog computation where mass and surface texture were the inputs and liquid volume was the output. To the modern engineer, this represents a mastery of open-loop control systems. There were no sensors to detect when the cup was full, nor was there a feedback mechanism to tell the valve to close based on the water level in the receiving vessel. The system relied entirely on the transient state of the coin. This required the manufacturing of the internal components to be exceptionally smooth and resistant to corrosion. If the fulcrum was too stiff, the coin would not tip the lever, resulting in a failure of service that could anger a worshipper. If the pan was too shallow, the coin would slide off too quickly, dispensing only a few meager drops. Hero had to calculate the angle of repose, the steepest angle at which a material remained stable, to ensure the coin would eventually slide off, allowing the counterweight to snap the system shut. This is the definition of reliability in mechanical engineering, a system that returns to its neutral state without external assistance, ready for the next cycle immediately. The valve mechanism itself demonstrates a keen understanding of hydrostatics. Hero likely employed a conical plug, known as a poppet valve in modern terminology, which sat flush against a matching seat. This design utilized the weight of the water itself to help maintain the seal. As the water pressed down on the plug, it reinforced the closure, preventing leaks that would otherwise drain the reservoir and waste the sacred resource. When the lever lifted the plug, it had to overcome not just the weight of the mechanism, but the hydrostatic pressure of the water column above it. This required a delicate balance between the sensitivity of the coin plate and the heaviness of the counterweight. If the counterweight was too heavy, the coin wouldn't lift the plug. If it was too light, the valve wouldn't seal tightly enough to stop the drip. The fact that this device functioned reliably in a public setting suggests a level of precision manufacturing that rivals the clockmakers of the Renaissance. Placing this device in a bustling temple courtyard fundamentally altered the economic landscape of the sanctuary. In the 1st century, Alexandria was a commercial and intellectual capital, and its religious institutions were not exempt from the pressures of the market. Temples were complex organizations that required significant revenue to maintain structures, fund festivals, and support the priesthood. Traditionally, the distribution of holy water required a priest or an attendant to be physically present, accepting donations and ladling out water from a basin. This human interaction created a bottleneck. It was slow, prone to human error, and susceptible to corruption or theft by the attendants themselves. Hero's automation solved the problem of scalability. By replacing the attendant with a bronze box, the temple could service hundreds of worshippers an hour, creating a continuous stream of revenue with zero labor costs. This innovation speaks to a sophisticated economic mindset, where efficiency was prioritized alongside piety. The machine enforced a standardization of the transaction that human attendants could not match. In a manual system, a priest might give more water to a wealthy patron or a friend, and less to a stranger. The machine, however, was impartial. It introduced the concept of the standard unit to religious commerce. Every 4 drachma coin purchased the same mechanical action, creating a uniform product experience. This is the bedrock of modern commerce, the guarantee of a standardized product for a standardized price, executed without human variation. Hero of Alexandria did not just invent a water dispenser, he invented the automated retail transaction, effectively turning the temple into a vending space where spiritual goods could be acquired with the same speed and predictability as buying grain. This shift toward automation also introduced a profound social change in how people interacted with the divine. For the first time, a religious ritual became a private transactional exchange between a human and a machine. The worshipper did not need to catch the eye of a priest, wait for a blessing, or engage in social pleasantries. They simply needed the correct hardware, a coin of sufficient weight. This depersonalized the experience, stripping away the social hierarchy that usually governed temple interactions. It suggested that the gods were accessible to anyone with the means to pay, democratizing the ritual through technology. The machine did not care about the social status of the user, only the physical properties of their money. In a society deeply stratified by class, caste, and citizenship, this mechanical neutrality was a radical concept. It replaced the judgment of the priest with the judgment of the balance beam. The lineage of this device is directly traceable to the turnstiles, parking meters, and snack machines of the 21st century. The fundamental logic remains unchanged. When you insert a credit card or a coin into a modern vending machine, you're engaging in the same mechanical dialogue that Hero scripted 2,000 years ago. The validation of payment followed by the timed release of a service. Hero's device even anticipated the concept of fraud detection. If a worshipper attempted to use a coin that was too light, perhaps a lower denomination, or a counterfeit shaving, the lever would not tip and the valve would remain sealed. This was an early form of physical security, enforcing the economic value of the product through the laws of physics. The machine acted as an impartial arbiter of value, rejecting insufficient inputs without argument or negotiation. However, the question remains, why did this technology not expand beyond the temple walls? Why did the Romans not have vending machines for bread, wine, or oil in their forums? The answer lies in the specific properties of the product. Holy water is a liquid, easily controlled by a valve, and it has high value relative to its volume, but low spoilage risk. Dispensing solid food requires complex escapement mechanisms to separate one loaf or apple from another, a mechanical challenge far greater than opening a pipe. Furthermore, the economic incentive was unique to the temple. In the broader Roman market, slave labour was abundant and cheap. There was no pressing economic need to automate the selling of bread when a shopkeeper could simply force an enslaved person to stand at a counter for 12 hours a day. The temple machine existed because it added to the mystique of the location and solved a specific crowd control problem, not because the Romans were pursuing a general policy of labour reduction. Ultimately, Hero's vending machine stands as a monument to the path not taken in ancient engineering. It proves that the mechanical principles required for an automated economy, energy storage, logical gating and feedback loops, were already understood and mastered in the 1st century. The components of the industrial future were sitting on a pedestal in Alexandria, disguised as a religious novelty. It reveals a civilization that possessed the hardware of the modern world, but lacked the economic and social software to fully utilize it. The coin dropped, the water flowed, and the lever reset, echoing through history as a lonely prototype of a future that wouldn't arrive for another 1800 years. The device sits atop a simple tripod, a polished bronze sphere suspended in mid-air that appears, at first glance, to be a static piece of temple decoration. Beneath the sphere lies a sealed cauldron filled with water, and beneath that, a fire burns. As the temperature rises, the water inside the basin transitions into a high-pressure gas, expanding to 1,600 times its liquid volume. This invisible force rushes upward through 2 vertical pipes that double as the structural supports for the sphere above. The gas enters the hollow ball through a pivot joint, filling the chamber until it finds the only available exit points. 2 bent nozzles protruding from the sphere's equator, angled in opposite directions. When the steam screams out of these jets, the sphere begins to rotate. It accelerates rapidly, blurring into a continuous form, spinning solely on the power of thermal energy converted into kinetic motion. This is the Aeolipile, the wind ball, a working steam engine built 17 centuries before the Industrial Age. The operating principle of the Aeolipile is pure Newtonian physics, utilised long before Isaac Newton formulated his laws of motion. It relies entirely on the 3rd law. For every action, there is an equal and opposite reaction. As the steam jets shoot outward from the nozzles, they exert a reactive force against the nozzle tips, pushing the sphere in the opposite direction. This is not a piston engine like the ones that would later drive locomotives, nor is it a pressure engine like the early pumps of the 18th century. It is a reaction turbine, conceptually identical to the propulsion systems used in modern jet aircraft and rocketry. The steam acts as the propellant, and the sphere acts as the rotor. Hero of Alexandria, in his treatise Pneumatica, described this mechanism not as a theoretical abstraction, but as a tangible machine, providing instructions that allow for its precise replication today. The genius lies in the vectoring of the thrust. By bending the nozzles at right angles to the radius of the sphere, the linear force of the escaping steam is converted efficiently into rotational torque. Technically, the steam generation system represents a closed-loop pressure vessel, a significant metallurgical challenge for the 1st century. The cauldron had to be airtight to prevent pressure loss, yet strong enough to withstand the buildup of steam without exploding. The vertical pipes supporting the sphere served a dual function, acting as both the structural frame and the steam delivery conduit. One of the most critical components was the pivot joint where the stationary pipe met the rotating sphere. Hero's design utilised a sleeve joint that had to be loose enough to allow the sphere to spin freely, but tight enough to prevent the valuable steam from leaking out before it reached the nozzles. This required a level of precision manufacturing that rivals modern machining, as a poor seal would result in a drastic loss of pressure, rendering the device motionless. The steam entering the sphere acted as a reservoir of potential energy, maintained at a constant pressure by the boiling water below, ensuring a steady stream of propulsion as long as the fire burned. When modern engineers and archaeologists reconstruct the Aeolipile using the specifications found in Hero's manuscripts, the results are often startlingly visceral. The machine does not merely spin, it achieves rotational speeds that can exceed 1,500 revolutions per minute. The sound is a high-pitched mechanical whine, accompanied by clouds of condensing vapour. These experiments reveal that the device was capable of generating significant speed, but they also expose its primary mechanical limitation, torque. While the Aeolipile spins furiously when unloaded, the moment any resistance is applied, such as a belt to drive a pulley or a gear to lift a weight, the rotation slows dramatically. The reactive force of the steam jets, while fast, lacks the sheer pushing power of a piston. The sphere has very little inertia compared to the friction it would encounter in a practical application. Furthermore, the consumption of fuel and water in these reconstructions is voracious. Without a condenser to recycle the steam back into water, the cauldron boils dry in minutes, requiring the machine to be stopped and refilled, which breaks the thermal cycle. The construction materials dictated both the function and the limitations of the engine. Roman artisans worked primarily in copper, bronze, and soldered lead. While bronze is an excellent material for casting complex shapes like the hollow sphere and the bent nozzles, it acts as a heat sink. As the steam travels from the cauldron through the pipes, the metal structure absorbs a significant amount of thermal energy, causing some of the steam to condense back into water before it ever leaves the jets. This thermal inefficiency means that a massive fire is required to maintain enough pressure for operation. Additionally, the metallurgy of the time could not produce alloys capable of withstanding the extreme pressures required to make a reaction turbine truly efficient. If the fire was stoked too hot to increase the torque, the soldered joints of the cauldron would likely melt or burst, destroying the engine. The Aeolipile existed at the very limit of what ancient materials science could sustain. Despite these limitations, the Aeolipile remains a functioning prototype of a steam turbine. The question that haunts historians of science is why this invention remained a curiosity. It sat in the intellectual inventory of the Roman Empire, a civilization that needed to pump water out of mines, grind grain for millions of citizens, and transport goods across vast distances. The Aeolipile offered a theoretical solution to all these problems. A scaled-up version, perhaps geared down to trade speed for torque, could have turned a millstone or lifted a bucket chain. Yet, it was never adapted for industrial work. It remained a philosophical toy, used perhaps to demonstrate the principles of pneumatics to students or to entertain guests at a symposium. The gap between the invention of the steam engine and the application of steam power is not technological, but conceptual and economic. The failure of the Aeolipile to trigger an industrial revolution in antiquity is best explained by the social structure of the Roman world. The Roman economy was built on the foundation of muscular energy, specifically the forced labour of enslaved people and the low-wage labour of the poor. When a mine owner needed to clear water from a shaft, the solution was not to build a complex, fuel-hungry, and potentially dangerous copper machine. The solution was to purchase more slaves to work the baler buckets. There was no economic pressure to save labour because labour was the most abundant resource available. Innovation is often driven by scarcity, and in a society where human effort was cheap and expendable, the high capital cost of developing thermal engines made no financial sense. The Aeolipile was a solution looking for a problem that the Romans did not believe they had. Furthermore, the scientific mindset of the era differed fundamentally from the utilitarian approach of the modern world. For Hero and his contemporaries, the goal of mechanics was often to mimic nature or produce wonder, thaumatur, rather than to increase industrial output. The Aeolipile demonstrated the presence of the divine element of air and the transformative power of fire. It was a proof of concept for the laws of nature, not a prototype for a factory. The idea that heat could be converted into work was visible to them, but the concept of work as a measurable, mechanizable output distinct from human or animal effort had not yet fully formed. The steam engine spun rapidly in the courtyard of the Serapeum, surrounded by the greatest minds of antiquity, yet it remained isolated from the economy, a premature artifact waiting for a world that valued fuel over flesh. In the end, the Aeolipile stands as the ultimate testament to the non-linear nature of progress. It proves that the mechanical invention of the steam engine preceded the cultural invention of industry by nearly 2 millennia. The components were all there: the fire, the water, the boiler, and the jet. The knowledge was codified, written down, and copied in libraries. But without the convergence of metallurgy, economic necessity, and a shift in how society viewed labour, the sphere simply spun in place. It serves as a stark reminder that technology alone is not enough to change history. It requires a civilization ready to receive it. The steam dissipated into the Mediterranean air, the fire died down, and the bronze sphere came to a rest, leaving the gears of industry locked for another 1500 years. The scattered remains of the Antikythera Mechanism, the corroded vessels of the Baghdad Battery, and the fragmented descriptions of Zhangheng's Seismoscope present a haunting paradox of history. We possess physical proof that the ancient world had mastered the fundamental principles of steam power, complex gearing, electrochemistry, and even nanotechnology. Yet these breakthroughs never coalesced into a sustained industrial revolution. The primary barrier was not a lack of intelligence or ingenuity, but the crushing weight of an economic system built on the backs of human beings. In the Roman Empire and the Han dynasty, the sheer abundance of cheap labour distorted the incentives for technological adoption. When a mine owner or a wealthy estate holder needed to increase production, the rational economic choice was not to invest in a costly, experimental machine that might break, but to purchase more slaves or hire more peasant labourers. The Aeolipile could spin at 1,500 revolutions per minute, but as long as a human life was cheaper than the bronze and fuel required to build a steam engine, there was no market force to drive the transition from muscle to machinery. This economic reality created a low equilibrium trap, where innovation was celebrated as art but neglected as utility. The Antikythera Mechanism demonstrates that Greek engineers were capable of manufacturing bronze gears with a precision that rivals modern watchmaking, effectively creating an analog computer to track the cosmos. However, this level of craftsmanship was likely the result of a singular master working for a wealthy patron, rather than a prototype for mass production. Without a middle class to purchase standardized goods, there was no demand for factories. The technology remained trapped in the realm of the masterpiece, a singular object of wonder, intended to impress a king or a god, rather than a tool to uplift an economy. The Lycurgus cup reinforces this limitation. Its dichroic glass relied on the precise suspension of gold and silver nanoparticles, a feat of chemistry that was likely achieved through secretive, empirical recipes passed down within a single workshop. Because these techniques were treated as guarded trade secrets, rather than scientific principles to be published and shared, they could not be scaled up or applied to other industries. Material limitations further arrested the development of these early technologies. While the theoretical understanding of steam and pneumatics was advanced, the metallurgy of the time struggled to contain the high pressures necessary for true industrial work. Hero of Alexandria could build a spinning sphere, but building a boiler capable of driving a locomotive requires high-quality steel and precision manufacturing that simply did not exist. The iron of the ancient world was often too brittle or too soft for high-stress applications, and the fuel source was primarily wood, which lacks the energy density of the coal that later powered the factories of the 19th century. Similarly, the Baghdad Battery proves that the Parthians understood the galvanic principle, but without the ability to draw copper into miles of fine wire, or the materials to create efficient insulators, electricity could not be transmitted or used for anything beyond localized electroplating. The ancients had the engine, but they lacked the chassis, the fuel, and the infrastructure to make it run. The fragility of knowledge preservation also played a catastrophic role in stalling progress. In the modern era, scientific discoveries are disseminated through journals and standardized education, creating a collective base of knowledge that is difficult to destroy. In the ancient world, advanced engineering was often concentrated in the hands of a few court astronomers, temple priests, or imperial bureaucrats. Zhang Heng's seismoscope was a brilliant application of inertia and mechanical triggers, but it was an instrument of the state designed to serve the emperor's administration. When the Han dynasty collapsed, the institutional support for such devices vanished, and the specific knowledge of its internal mechanism was lost for nearly 2 millennia. There was no backup of this data in public libraries or foreign universities. When a civilization fell, its technology often died with it, forcing humanity to reinvent the wheel, or the gear, or the battery centuries later. Cultural and philosophical attitudes toward the natural world further widened the gap between invention and industry. For the Hellenistic Greeks and logic-obsessed Romans, the highest form of intellectual pursuit was theoretical and abstract. Geometry and astronomy were considered noble because they dealt with the eternal heavens, while mechanics and engineering were often viewed as banausic, or vulgar, because they involved manual labour and dirt. Hero of Alexandria used his mastery of hydraulics and pneumatics to create automatic doors for temples and coin-operated holy water dispensers, because the goal was to inspire awe and reinforce religious authority, not to automate the weaving of cloth. The miracle of the machine was more valuable than its utility. In this worldview, using the forces of nature to do mundane work was almost a degradation of the science. The gods were to be simulated and studied, not put to work on an assembly line. Ultimately, the failure of the Industrial Revolution to ignite 2,000 years ago reveals that technology alone is insufficient to change history. The components were all there: the gears of Antikythera, the steam of the Aeolipile, the electricity of Baghdad, and the chemistry of the Lycurgus cup. Yet, these inventions remained isolated islands of genius in a sea of traditionalism. They lacked the converging forces of capitalism, property rights, expensive labour, and the scientific method that would eventually spark the Great Divergence in Europe. We look back at these artifacts not as failures, but as premature triumphs, signals from a timeline where the mind outpaced the market. They stand as a testament to human ingenuity, but also as a solemn reminder of how easily the momentum of progress can be lost when the social and economic foundations are not ready to support the weight of the future. It is a chilling realization that for centuries, the blueprints for the modern world sat gathering dust in temple archives or sinking to the bottom of the Mediterranean. The silence between the Antikythera Mechanism and the Renaissance suggests a terrifying fragility to human knowledge, proving that advancement is not a guaranteed straight line but a precarious climb, easily reversed by societal collapse. When we marvel at these ancient precursors, we see the ghosts of a future that never came to pass, a potential history that withered because civilization favoured conquest over commerce. These objects strip away our modern arrogance to reveal that we are not the first masters of complexity, merely the first to successfully industrialize it. The spinning brass sphere of Hero's Aeolipile and the intricate gears of the Antikythera Mechanism prove that the ancient world possessed the intellectual capacity for an industrial revolution, yet the smokestacks of industry never rose over the Roman Forum or the Library of Alexandria. The primary culprit for this arrested development was not a lack of ingenuity, but an abundance of cheap human bodies. In a society where labour could be coerced from millions of enslaved people for the mere cost of subsistence, the economic incentive to invent labour-saving devices was effectively non-existent. The ruthless arithmetic of the ancient economy dictated that a human being, captured in war and stripped of rights, was a far cheaper and more versatile engine than any steam-powered contraption a mathematician could devise. This economic reality created a formidable barrier to the adoption of complex machinery. innovation requires significant upfront capital investment, maintenance, and the risk of failure. In the 18th century, British industrialists invested in steam engines because the cost of labour was high and coal was cheap, creating a desperate need for efficiency. The Roman context was the exact inverse. With a steady influx of captives from campaigns in Gaul, Dacia, and North Africa, the supply of labour was artificially inflated and the cost depressed. A wealthy landowner looking to crush olives or grind grain had two choices: commission a complex, fragile, and expensive watermill that required specialised engineering to build and maintain, or purchase 50 slaves who could be worked to death and easily replaced. For the rational Roman capitalist, the path of least resistance was always paved with human misery rather than mechanical ingenuity. The reliance on slave labour did more than just skew the balance sheets. It fundamentally altered the social perception of mechanics and engineering. Because manual labour was the domain of the enslaved, the act of working with one's hands was stigmatised as degrading for the educated elite. The great minds of the era, men like Plato, Aristotle, and Cicero, viewed the Banosic arts, practical mechanical work, as vulgar and beneath the dignity of a philosopher. Consequently, the smartest men in the empire dedicated their lives to rhetoric, law, and abstract geometry, rather than the gritty, practical problems of efficiency and production. The separation of the mind that understood the theory from the hand that performed the work meant that scientific principles rarely crossed over into the workshop. Hero of Alexandria could write about pneumatics and steam pressure, but the people who might have benefited from a steam pump, the miners and farmers, were socially and intellectually cut off from his library. There is a telling historical anecdote concerning the Emperor Vespasian that perfectly encapsulates this systemic resistance to automation. When an engineer approached the emperor with a novel device that would allow heavy stone columns to be transported to the capital with minimal effort and cost, Vespasian rewarded the man for his genius but refused to use the machine. His reasoning was explicitly political and social. "You must let me feed my poor commons." The emperor feared that if a machine did the work of thousands, the resulting unemployment among the free poor and the idle nature of the enslaved would lead to social unrest. In this worldview, inefficiency was a feature, not a bug. The labour-intensive nature of construction and agriculture was seen as a necessary tool for social stability, keeping the masses occupied and dependent on the state or wealthy patrons for their daily bread. This fear of labour-saving technology created a feedback loop of stagnation. Because there was no demand for machines to replace human muscle, there was no iterative cycle of improvement. The steam engine of the 18th century did not emerge fully formed. It was the result of decades of tinkering by mechanics, trying to solve the specific problem of pumping water out of deep coal mines. In the ancient world, when a mine flooded, the solution was not to invent a better pump, but to send in more slaves with buckets, accepting their inevitable deaths as an operating cost. Without the economic pressure to solve practical problems through engineering, the Aeolipile remained a temple curiosity rather than becoming the prototype for a locomotive. The gears of the Antikythera Mechanism tracked the heavens, but they were never adapted to run a textile loom. The stagnation was also reinforced by the flexibility of human labour compared to the rigidity of early machines. A slave could harvest crops in the autumn, repair fences in the winter, and serve as a household servant in the spring. A machine, by contrast, was single-purpose. In an era before standardized parts and mass production, a broken machine was a catastrophic loss of capital. If a gear snapped in a watermill, the entire operation halted until a specialized craftsman could be found to forge a replacement. If a slave fell ill or died, the labor market provided an immediate substitute. The human machine was self-repairing to a degree, self-fueling, and infinitely reprogrammable. This grim versatility made biological energy the gold standard of the ancient economy, rendering mechanical alternatives unattractive to anyone but the most eccentric experimenter. It is haunting to consider that the very institution that built the grandeur of Rome, slavery, was the same force that prevented it from achieving the technological escape velocity necessary to transcend the ancient world. The reliance on coerced labour acted as a narcotic, dulling the civilization's drive for progress. While Roman engineers were masters of static structures like aqueducts, roads, and domes, they largely ignored dynamic power. They conquered space with concrete and stone, but they failed to conquer time with speed and mechanization. The intellectual leaps made by Zhang Heng in China with his seismoscope or the craftsmen of the Lycurgus cup were isolated sparks that failed to ignite a larger fire because the fuel of economic necessity was missing. The tragedy of this lost opportunity is quantified not just in the centuries of technological delay, but in the immense human suffering that continued unchecked. Had the economic dynamics been different, had labour been expensive and scarce, the brilliant minds that designed the automata of Alexandria might have turned their attention to threshing machines or steam pumps. Instead, the smart systems described by Hero remained toys for the amusement of the elite, dispensing holy water and opening temple doors to evoke wonder rather than doing the heavy lifting of civilization. The ancient world proved that scientific knowledge is necessary but not sufficient for an industrial revolution. It requires a society that values the machine more than the master's whip. We are left with the realization that the technological timeline of humanity is not a ladder, but a branching path where the wrong turn can lead to a dead end that lasts for a millennium. The ancient engineers had unlocked the secrets of the atom, the gear, and the steam jet, but they were trapped in a social structure that had no use for their most revolutionary ideas. The gears stopped turning not because the mathematics failed, but because the market for innovation was suffocated by the availability of the oppressed. The silence of the Aeolipile is the sound of a civilization choosing the ease of tyranny over the challenges of transformation. Chapter 18: Knowledge Transmission and Loss. Fire is the most efficient editor of human history, but it is not the only one. While the burning of the Library of Alexandria serves as the archetypal tragedy of lost knowledge, the disappearance of advanced ancient technology was rarely a singular dramatic event. Instead, it was a slow, agonizing erosion caused by the fragility of the medium and the secrecy of the maker. The survival of a device like the Antikythera Mechanism is a statistical anomaly, a winning lottery ticket in a graveyard of melted bronze and rotted wood. Most technical knowledge in the ancient world was not stored in libraries or inscribed on stone tablets. It was locked within the muscle memory of master craftsmen and the oral traditions of closed guilds. When a civilization destabilizes, that living chain of transmission is the first thing to break. The fate of Zhang Heng's seismoscope illustrates the vulnerability of state-sponsored science during times of political upheaval. This device was not a commercial product, but an imperial instrument, maintained by the court for the specific purpose of governance. When the Han Dynasty collapsed, the bureaucratic infrastructure that supported such complex engineering collapsed with it. The physical device was made of high-quality bronze, a material that retains its value regardless of the shape it takes. To a starving population or a conquering warlord, a complex vessel capable of detecting distant earthquakes is far less useful than the coinage or weaponry that could be forged from its melted carcass. The intricate internal pendulum system, calibrated to the inertia of the Earth, was likely dismantled for scrap. Although historical texts describe the external appearance and the function of the machine, the schematics, the precise engineering data required to replicate the trigger mechanism, were lost. The knowledge did not disappear because the science was disproven. It disappeared because the institution that protected it ceased to exist. This pattern of loss is compounded by the nature of pre-industrial trade secrets. The creators of the Lycurgus cup did not publish papers on the optical properties of gold and silver nanoparticles. They were artisans who had discovered a specific empirical process through trial and error. This knowledge was likely proprietary, guarded jealously by a specific workshop to maintain a monopoly on the luxury market. The production of such dichroic glass required not just the know-how, but a precise supply chain of specific minerals and salts. When the Roman trade networks began to fracture, the flow of raw materials from distant provinces was interrupted. If a glassmaker in Rome could no longer obtain the specific type of antimony or the exact gold salts required for the colloidal mixture, the recipe would fail. After a generation of failures, the formula would be dismissed as a myth or a forgotten magic. The technology dies not because the artisans forgot how to blow glass, but because the delicate ecosystem of trade and logistics required to support high-level nanotechnology had disintegrated. Religious and cultural shifts also played a significant role in filtering what knowledge was preserved and what was discarded. As the intellectual centres of the Mediterranean transitioned from the polytheistic, mechanistic worldview of the Greeks and Romans to the theological focus of early Christianity and later Islam, the priorities of scholarship shifted. The automata of Hero of Alexandria, once celebrated as marvels of pneumatic engineering, were increasingly viewed as trivial curiosities or, in some cases, suspicious relics of pagan temple trickery. However, the transmission of knowledge is rarely a straight line. While Europe entered a period of stagnation regarding mechanical engineering, the texts of Hero and the knowledge of Greek astronomy found a lifeline in the Islamic Golden Age. Scholars in Baghdad did not merely translate these works, they built upon them. The survival of the principles behind the Aeolipile and the water clocks is largely due to the House of Wisdom and similar institutions that recognize the value of Hellenistic mechanics, even if the immediate economic application was still lacking. The Baghdad Battery offers a different perspective on lost technology, one where the knowledge may have been so niche that it never entered the written record at all. If these jars were indeed used for electroplating gold onto copper, the process would have been the closely guarded secret of jewelers. There was no incentive to share the secret of how to fake solid gold with a thin layer of plating. In fact, there was every economic incentive to keep it hidden. In a culture of oral tradition and trade secrecy, the death of a master craftsman without a competent heir means the extinction of the technology. It is entirely possible that the knowledge of galvanic cells was discovered and lost multiple times in history, emerging in a workshop in Mesopotamia, only to vanish when the family line ended or when the market for plated goods dried up. Unlike the Antikythera Mechanism, which was a product of high theory and mathematics, the battery was likely a product of workshop alchemy, vulnerable to the silence of the unwritten. The recovery of these technologies relies on the serendipity of disaster. The Antikythera Mechanism survived only because it sank. Had the ship reached its destination in Rome, the device would have eventually broken, been judged too difficult to repair, and recycled for its valuable bronze. The sea, by claiming the ship, preserved the metal in a thick crust of concretion, hiding it from the recycling drives of the next 2,000 years. This paradox defines archaeology. We often know more about the failures of the past, the ships that sank, the cities buried by volcanoes, than the successes that remained in circulation until they wore out. The jagged landscape of ancient technology is jagged partly because we are looking at the survivors of a massive attrition rate. For every Antikythera mechanism that we find, there were likely dozens of other geared devices, astrolabes, planetariums, hodometers, that were successfully delivered, used for a century and then melted down to make belt buckles or cannonballs during the Middle Ages. Ultimately, the story of ancient technology is a lesson in the fragility of civilization's hard drive. We tend to view progress as a cumulative process, where each generation builds on the last, but the archaeological record shows that progress is often cyclical and prone to catastrophic resets. The steam turbine, the analog computer, and the battery were all invented, functioned, and then were forgotten. The transmission of knowledge requires more than just the existence of a brilliant idea. It requires a stable society to value it, an economy to sustain it, and a medium durable enough to carry it across the centuries. When we look at the corroded gears of the Antikythera Mechanism or the silent shell of the Lycurgus cup, we are not just seeing ancient inventions, we are seeing the survivors of a great silence, artifacts that barely managed to whisper their secrets to the future before the darkness closed in. The history of innovation is not a straight line ascending toward perfection, but a complex branching structure where viable paths are often abandoned and forgotten. The rediscovery of the Antikythera Mechanism and the Lycurgus cup forces a confrontation with the uncomfortable reality that technological sophistication does not guarantee survival. These artifacts are not merely curiosities or puzzles to be solved. They are case studies in the fragility of high-level engineering. When we analyse the differential gears of the Antikythera Mechanism, we are looking at a mechanical solution to a mathematical problem that would not be replicated in Europe for another 18 centuries. This gap in history suggests that the modern assumption of inevitability, that once a technology is invented, it stays invented, is fundamentally flawed. The lesson from the Aegean seabed is that knowledge behaves less like a permanent library and more like a living organism. Without a supporting ecosystem, it dies. This insight has profound relevance for contemporary technology, particularly in the field of computing. We currently rely almost exclusively on digital systems that require vast amounts of electricity and complex semiconductor supply chains. However, the Antikythera Mechanism demonstrates the power of analog computing. It processed information about celestial cycles not through binary code, but through the physical geometry of bronze teeth. In an era where energy efficiency is becoming critical for computing, modern engineers are revisiting analog processes for specific tasks, such as neural networks and pattern recognition. The ancient Greek approach of embedding the algorithm directly into the hardware offers a model for creating robust, low-power systems that can operate for centuries without a battery change or a software update. The resilience of the mechanism, which retained its information despite spending 2,000 years underwater, stands in stark contrast to modern digital storage media, which can degrade in a matter of decades. Beyond computing, the material sciences of the ancient world offer templates for sustainable manufacturing. The Lycurgus cup is a masterclass in what we now call photonics and plasmonics. The Roman artisans did not use toxic synthetic dyes or fading pigments to achieve the cup's colour-shifting properties. They used the structural manipulation of matter at the atomic scale. By embedding gold and silver nanoparticles into the glass matrix, they created a material that interacts with light physically, rather than chemically. Today, this specific field of study is revolutionizing medical diagnostics. The same principle that turns the Lycurgus cup from green to red is now being used to develop biosensors that change color in the presence of specific pathogens or DNA strands. The Romans achieved this through empirical craft, while we achieve it through theoretical physics, yet the result is identical. It suggests that the future of coloring and sensing may lie in returning to these non-fading structural methods rather than relying on the chemical industries that currently dominate manufacturing. The environmental implications extend to the mysteries of the Baghdad Battery. While the voltage produced by these clay jars was low, the chemistry was surprisingly benign compared to modern standards. A copper cylinder, an iron rod, and an electrolyte like vinegar or grape juice constitute a battery that is fully biodegradable. In our current rush to electrify the global economy, we face a looming crisis of lithium-ion battery waste and heavy metal pollution. The Parthian approach, utilizing common non-toxic materials to manipulate electron flow, points toward a philosophy of appropriate technology. It challenges the modern obsession with high energy density at any environmental cost. If the goal is merely to plate gold or perform a simple chemical reaction, the ancient solution is infinitely more sustainable than the modern equivalent. It serves as a reminder that low-tech solutions are often more harmonized with the natural world than high-tech ones. However, the most critical lesson lies not in the hardware, but in the sociology of adoption. The failure of Hero of Alexandria's Aeolipile to spark an industrial revolution is a stark warning about the relationship between economics and invention. The steam engine existed, the physics was sound, and the prototype was functional, yet it remained a toy because the social structure of the Roman Empire did not demand it. With an economy built on the backs of enslaved people, there was no financial incentive to invest in labour-saving machinery. This dynamic mirrors modern debates surrounding automation and artificial intelligence. Technology is never adopted in a vacuum. It is filtered through the economic realities of the time. Just as cheap labour suppressed the steam engine in the 1st century, modern economic structures often delay the implementation of superior technologies, such as renewable energy systems or efficient mass transit, because they threaten established profit models. The Aeolipile proves that technical feasibility is only half the battle. Without a socio-economic architecture that values the innovation, even the most revolutionary machine will remain a curiosity. Furthermore, the passive nature of ancient high-tech offers a blueprint for resilience. Zhangheng's Seismoscope monitored the Earth for tremors 24 hours a day, year after year, without consuming a single watt of power. It utilized the potential energy of gravity and the inertia of a pendulum, waiting dormant until the moment it was needed. Modern sensor networks require constant power, maintenance, and data connectivity. In a future where energy security may be volatile, the concept of purely mechanical, passive sensing devices becomes incredibly attractive. We are relearning that there is elegance and security in systems that do not rely on the grid. The drag-link mechanisms and inverted pendulums of the Han Dynasty are not primitive. They are triumphs of efficiency, achieving their goal with the absolute minimum input of energy. Ultimately, these rediscovered principles challenge our definition of advanced. We tend to equate advancement with complexity, power consumption, and miniaturization. Yet the longevity of these artifacts suggests that true advancement includes durability and independence. A computer that works for 2,000 years is, in one specific metric, superior to a smartphone that lasts 3. The future of technology may not lie in continuing the trajectory of disposable high-energy devices, but in synthesizing modern knowledge with ancient durability. We might envision a future where critical data is stored on etched metal discs like the Antikythera gears, where sensors operate on the passive mechanics of Jiangheng, and where materials are coloured by the structural nanotechnology of the Lycurgus cup. The study of these artifacts removes the hubris from our modern perspective. We are not the first to harness the electron, the first to build a computer, or the first to manipulate matter at the nanoscale. We are simply the latest to try. The silence that followed the fall of Rome and the collapse of the Han Dynasty serves as a reminder that scientific progress is a torch that must be actively protected, not a sun that rises automatically. By understanding how these technologies worked and why they were lost, we gain the perspective needed to ensure that our own innovations do not become the baffling archaeological mysteries of the future. The jagged landscape of history shows us that the climb is steep, the footing is treacherous, and the summit is never guaranteed. The true revolution in understanding the ancient world no longer takes place solely in the trenches of an excavation site, but inside the sterile environments of high-energy physics laboratories and engineering workshops. When the Antikythera Mechanism was first recovered from the seafloor, it was nothing more than a calcified lump of bronze and sediment, indistinguishable from the surrounding debris. Traditional cleaning methods would have destroyed the delicate gear trains hidden within, forever erasing the evidence of its complexity. It was only through the application of X-ray computed tomography, using systems originally designed for inspecting the structural integrity of turbine blades, that researchers could virtually slice through the artifact. This non-invasive dissection revealed thousands of characters of text and the precise tooth counts of gears that had not seen the light of day in 2 millennia. This technology allows us to reverse engineer the mind of the inventor without scratching the surface of the object, turning a corroded rock into a readable blueprint of ancient genius. Visual inspection, however, only tells half the story. To truly understand the engineering constraints of the Han Dynasty or the Parthian Empire, researchers must turn to experimental archaeology. This discipline moves beyond theoretical models and involves physically reconstructing devices using the materials and tools available at the time. When researchers reconstructed Jiangheng's seismoscope, they did not just build a model that looked correct, they built a functional sensor that had to obey the laws of inertia and friction. By testing these replicas against simulated seismic waves, they confirmed that the inverted pendulum mechanism was not merely symbolic, but a tuned mechanical filter capable of distinguishing between a carriage passing by and a distant tremor. This build to understand approach forces historians to confront the physical realities of material weight, tolerance, and manufacturing variance that the original inventors faced, proving that these devices were not just conceptual but operational. Similarly, the secret of the Lycurgus cup remained invisible to the naked eye for centuries. To an observer in the 1950s, the glass was simply a beautiful oddity. It required the resolution of transmission electron microscopy to detect the gold and silver nanoparticles suspended in the colloidal matrix. This level of analysis shifts archaeology from a study of shape and form to a study of atomic structure and chemical composition. We now know that Roman artisans were not just mixing colours, but manipulating matter at the scale of billionths of a metre. These tools strip away the magic of the ancient world and replace it with quantifiable material science, proving that the results were intentional rather than accidental. In the case of the Baghdad Battery, trace element analysis and mass spectrometry are the only ways to detect microscopic residues of acidic electrolytes like vinegar or lemon juice, which would have evaporated thousands of years ago. These chemical ghosts are the only evidence we have to confirm the function of the vessel as a galvanic cell. The complexity of these discoveries has forced a dismantling of academic silos. The study of the Antikythera Mechanism could not be solved by archaeologists alone. It required a coalition of astronomers to calculate the eclipse cycles, mathematicians to decipher the gear ratios, and philologists to read the faint inscriptions. This interdisciplinary reliance is becoming the standard for investigating ancient technology. A chemist is needed to analyse the corrosion patterns on copper cylinders, while a mechanical engineer is required to understand the pressure valves and siphons in Hero's automata. We are learning that to study the history of science, one must actually understand the science itself. The interpretative framework of art history is no longer sufficient when analysing a differential gear or a steam turbine, requiring a fusion of the humanities and the hard sciences to fully grasp the capabilities of our ancestors. Despite these advancements, the archaeological record remains a fragmented puzzle where the most crucial pieces are often the first to vanish. We rely heavily on the survivorship bias of materials. Bronze, gold and ceramic endure, while wood, leather and papyrus rot away. The automata of Alexandria likely used complex systems of ropes, pulleys and leather seals that have long since disintegrated, leaving us with only the metal shell and a few vague descriptions. This creates a ghost machine problem, where we possess the durable components but lack the soft connective tissue that made them function. Reconstructing these missing links requires a careful balance of evidence and engineering logic, ensuring that modern biases about how a machine should work do not override the often counterintuitive solutions used by ancient engineers. We must be careful not to project our own industrial efficiency onto a world that may have prioritized aesthetics or ritual significance over raw output. The future of archaeological investigation lies in the digitization of the physical world and the application of artificial intelligence to fragmented data. Algorithms are already being trained to piece together shattered tablet fragments and predict missing text based on stylistic patterns, potentially recovering lost manuals or schematics for devices we currently do not understand. As scanning resolution improves, we may find trace evidence of wear patterns on gears that reveal exactly how often a device was used, or isotopic signatures that tell us exactly where the copper for a battery was mined. We are moving toward a holistic view of history where the artifact is treated as a solidified piece of data. The ultimate goal is to bridge the gap between the artifact and the artisan, realizing that the gap in intelligence between a Roman engineer and a modern scientist is non-existent. The only difference is the cumulative knowledge at their disposal. Through these methods, we are not just discovering objects, we are recovering the lost operating system of human civilization. The historical record is not a smooth upward slope of progress, but a landscape scarred by jagged peaks of brilliance and deep valleys of amnesia. We have traversed a timeline where the boundaries of what was considered possible for ancient engineers have been thoroughly dismantled by the artifacts themselves. The existence of the Antikythera Mechanism alone proves that the capacity for complex differential calculus and astronomical modelling existed over 2,000 years before the European Renaissance. This was not a primitive attempt at computing, it was a mature, calibrated system of 30 bronze gears that could predict the erratic orbital velocity of the Moon. Similarly, the Lycurgus cup demonstrates that Roman artisans had empirically mastered the manipulation of matter at the atomic scale, embedding gold and silver nanoparticles to create dichroic glass long before the concept of a nanometer existed in the scientific lexicon. These are not isolated curiosities or inexplicable out-of-place artifacts. They are the surviving debris of sophisticated technical ecosystems that once flourished and then vanished. This journey through the lost technologies of antiquity forces a re-evaluation of the very nature of invention. We often assume that once a technology is discovered, it is permanently added to the human toolkit. Yet the evidence suggests that knowledge is far more fragile than materials. The Baghdad Battery implies a working knowledge of electrochemistry and the ability to manipulate galvanic currents for gilding, yet this knowledge did not spark an electrical age in Parthian Persia. The principles were understood, the application was functional, but the societal infrastructure required to scale that invention into a grid or a communication system was absent. Innovation requires more than just a genius inventor. It requires an economic incentive, a stable political environment, and a culture that values mechanical efficiency over cheap labour. The failure of Hero of Alexandria's Aeolipile to trigger an industrial revolution serves as the most potent warning from the past. The physics of steam power were known, the rotary engine was built, and the concept of converting heat into motion was demonstrated in the heart of the Roman Empire. However, in an economy built on the backs of enslaved people, there was no financial motivation to invest in labour-saving machinery. The steam turbine remained a temple wonder and a parlour trick, because the social structure of the time stifled its potential. This reveals that technological stagnation is rarely caused by a lack of intelligence, but rather by a lack of necessity or economic viability. When a society becomes complacent with its current methods of production, even the most revolutionary inventions can be relegated to the status of toys, waiting centuries for a socio-economic climate that demands their utility. Modern innovators can draw profound lessons from these ancient successes and failures, particularly regarding resilience and sustainability. The devices that have survived for 2 millennia did so because they were built with robust analog principles that did not rely on fragile networks or constant updates. Zhang Heng's seismoscope monitored the Earth's tremors using the fundamental law of inertia and an expertly balanced pendulum. It required no power source, no maintenance code, and no external data stream. It simply waited for the ground to move. In an era where our own technology is increasingly dependent on rare earth minerals, global supply chains, and ephemeral digital infrastructures, the passive engineering of the ancients offers a blueprint for durability. There is immense value in designing systems that function through mechanical logic and material properties, like the structural colour of the Lycurgus cup, rather than relying solely on energy-intensive active components. Furthermore, the preservation of knowledge is revealed to be the single most critical factor in the continuity of civilization. The gap between the Antikythera Mechanism and the first mechanical astronomical clocks of the late Middle Ages represents 1,500 years of lost time. This dark age of technology was not a pause, but a regression, caused by the disintegration of the trade networks that supplied the raw materials and the collapse of the institutions that trained the master apprentices. The schematics for Zhang Heng's internal mechanism were lost not because they were flawed, but because the dynasty that guarded them fell. We are reminded that writing things down is not enough. The medium of storage must survive, and the ability to interpret that medium must be maintained. Today, as we store the sum of human knowledge on magnetic drives and servers that degrade within decades, the risk of a digital dark age parallels the loss of the Library of Alexandria. The ancients carved their most important data into bronze and stone, and even then, we only have fragments. The future of rediscovering ancient technology lies in the realization that we have likely found only a fraction of what once existed. The Mediterranean floor is a vast, unexcavated museum, holding thousands of shipwrecks that may contain other mechanisms as complex as the Antikythera device. As our tools for underwater exploration and non-invasive scanning improve, we will likely find that the anomalies we discuss today were actually standards of their time. We are moving toward a future where artificial intelligence can analyze the corrosion on a lump of metal and reconstruct the gears that once turned inside it, or read the carbonized scrolls of Herculaneum to reveal lost treatises on pneumatics and optics. The cycle of innovation is not a line, but a loop. We are constantly rediscovering principles that were mastered by ancestors who looked at the same stars, felt the same earthquakes, and sought to harness the same physical laws. Ultimately, these artifacts serve as a humbling testament to human ingenuity. The mind that designed the differential gear in 100 BC is indistinguishable from the mind designing a spacecraft today. The difference lies only in the accumulated layers of shared knowledge. By studying these ancient machines, the steam engines that didn't power factories, the batteries that didn't light cities, and the computers that sank into the sea, we gain a clearer perspective on our own technological moment. We see that progress is not guaranteed, that science can retreat as well as advance, and that the most advanced machine is useless without a society that understands its value. The story of ancient technology is not just a history of objects, it is a history of potential, realizing that the future has happened before, and if we are not careful, the knowledge we possess today could once again become the mystery of tomorrow.